Hello, good evening everyone and welcome back to another session in this fluid mechanics revision session for GATE 2021. I'm Vikas Sir and I welcome you all to this session on revision of entire fluid mechanics part 2. So in the part 1 of the revision of fluid mechanics, we have covered the topics from fluid properties till fluid kinematics. Today we'll be completing the entire fluid mechanics revision. Hi Santosh Kumar, very good evening. Hi Ananta Saha, good evening, very good evening. Welcome to the session. So I'm back again with another session on this revision of fluid mechanics. So very good evening everyone and welcome to this session. Yes, I can see we are having many students live in this session. So those who are there in the YouTube channel, quickly join me for this session. Everyone. Shrikant Bodhi, very good evening, welcome to the session. So again we are going to revise the entire fluid mechanics. Today we are going to complete the revision of fluid mechanics actually, and we will definitely be assured that the revision will be completed of fluid mechanics. Not only revision of fluid mechanics will be there, but we'll be also solving around 24 plus questions, or we can say 20 plus questions will be there for practice from each and every topic. Okay, so basically it is a complete package for revision of the concepts and practice of the question for fluid mechanics subject. I hope you have watched my previous lecture of the revision of fluid mechanics that I have taken in the last, that is on 26th at the same time at 5 p.m. So I'm back again with another revision session. Everyone quickly join me for the session. Yes, very good evening everyone. Hi, good evening, Shrikant Bodhi. We are having only 6 students who are live. Come on, everyone, quickly join me for this session. I hope that you guys have already informed about this, that today we are having our revision session. So today we have our revision session. Yes. One part most of you have already attended. Today this is the second part of the revision session on fluid mechanics. So everyone quickly join me for this session. Hi Vikas Yadav, very good evening. Welcome to the session. Yes. Guys, those who are joining me for this session, please also give some time to like the session and also share the session so that we can have maximum participant can join this session for this amazing revision section on fluid mechanics. Hi Dinesh Kumar, very good evening. Welcome to the session. So everyone quickly join me for this session on refraction, self-refraction. Very good evening. So everyone, good evening to this session and welcome to this session. Weightage of FM and hydraulic machinery in the GATE 2021. Santosh Kumar, the weightage will be same. It will be around the total out of total technical weightage. It will be having weightage of around 8 to 9%. That is today's the complete weightage will be around 7 to 8 marks in the GATE 2021. Hitesh Arora, the revision of thermodynamics part 2 with practice of the questions will be on Monday, that is tomorrow at 7 p.m. So tomorrow at 7 p.m. will be upon last today the session I will try to complete at 8 p.m. not more than 8 p.m. Okay, because yesterday the session got very extended. It got extended much, but today we'll try to wrap up in 3 hours. Okay, that is the target. Let's see whether we are able to match our target or not. Okay. So good evening, everyone. Hi, Apan Raj. Good evening, Dinesh Kumar, Hitesh Arora. Today's topic, Dinesh Kumar, will be from fluid dynamics till the complete fluid mechanics will be completed along with fluid machinery, starting from fluid dynamics. Okay. Yes. So guys, those who have joined me for this session, please give some time to like the session also. Previous session had only concepts. No, Hitesh Arora, the previous session, if you are talking about thermodynamics, yes, the previous session of thermodynamics was only having concept. Okay, but on Monday, that is on 28th of December, I will take a practice session on thermodynamics where we'll be solving around 40 plus questions on thermodynamics. Okay, it will be just a practice session. So tomorrow will be a practice session for thermodynamics. Yes, hurry up guys, hurry up. Come on everyone. Quickly join me for this session. Yes. I hope you all of you have liked the session that I have taken yesterday. You have enjoyed the revision of fluid mechanics. Today also we'll be revising the fluid mechanics subject, and yes, definitely. Okay, let's see whether the session is extended or not. Okay, so those who have joined me for this session, please give some time to like the session and also share the session. And अगर आपने चैनल को सब्सक्राइब नहीं किया है, if you have not yet subscribed our channel, then please do subscribe the channel and press the bell icon. Okay. Yes, come on. The number of students are so less. You know the timing of the session. Still, you have not joined the session. Guys, so let's start the session. In the last lecture, I have given you a question for homework. Let me start the revision with my introduction first. I'm Vikas Sir. I have 5+ year teaching experience. I did my MTech in thermal engineering from Thapar University, which is in Patiala, a very beautiful city. I have mentored more than 10,000 plus aspirants for different GATE exams like GATE, Engineering Services and SSC JEE and other exams. My area of expertise includes subjects of fluid mechanics, thermal applied and heat transfer subject. If you want to score more than 60, yeah, definitely it is the right time, my dear. Yeah, if you want to score more than 60, definitely it is the perfect time. Not to start, but yes, if you have completed a bit of syllabus, then definitely you can score 60 plus if you follow proper strategy and proper schedule. Okay, so then you can score 60 plus marks. This was the homework question I have given. This was the homework question I have given for the last in the last class, and I don't know how many of you have solved this question. Hi Ayush Kumar Chaudhary, very good evening. Welcome to the session. Those who have joined me for this session, please also give some time to like the session and also share the session, because today the number of students are so less. I think some of the students are celebrating Sunday. There is much time for celebration. You can celebrate after GATE exam, right? When GATE exam will be over, you guys can definitely celebrate, do the celebration. But right time it's not the right time for celebration, because we have to study a lot. Very less time is left for the exam. So I'm just hoping that everyone, those who are present in the last lecture, will be joining today also. So I'm just expecting that. Although I have shared the session already on the Telegram group and on Gradeup app, but it's my request to all of you, those who have joined me for this session, please share this session also to your friends and to your classmates who are preparing for GATE 2021, so that they can also be informed about this amazing session. Math के लिए कोई series है क्या? Hitesh Arora, yes, there is a series for mathematics which is being taken by Rakesh Talreja sir. He is already taking a series on mathematics, so you can see that mathematics series is scheduled every day from at 10 p.m. on GATE Gradeup IT channel. Okay. Chaliye, let's start the session. Okay, tell me the answer for this question. The answer is option C. How can you solve this question? You have to find the approximate resultant total acceleration. They have given the velocity, that is t square plus 3y. U component of velocity and v component of velocity is 3t plus 3x. Because this component of velocity is given in x and y coordinates, then you have to find the acceleration in the x coordinate, that will be u times of del u by del x plus v times of del u by del y plus del u by del t, because they are also giving the value of time. You have to find the value of acceleration at time is equal to 2 seconds. Okay, so you have to find the total resultant acceleration. Total acceleration will be the root of acceleration in the x direction plus acceleration in the y direction. So this is the total acceleration in the x direction. Total acceleration in the y direction will be equal to the sum of, this is the convective, this is the local acceleration. This will be equal to u times of del v by del x plus v times of del v by del y plus del v by del t. Right? So I hope many of you have solved this question. The answer will be option C. Okay. This was the homework question I have given in the last lecture. Okay. So should I tell you the solution? Yes. So you have to find the value of du by dx. The du by dx will be equal to 0. Du by dy will be equal to 3. And du by dt will be equal to 2t. You have to find the du by dt as t is equal to 2. That will be 2 into 2 equal to 4. Similarly, you have to find the value of dv by dx. dv by dx will be equal to 3, dv by dy will be equal to 0, and dv by dt will be equal to 3. Because we have found all these things, you have to also find the value of total acceleration at point 3 and 2. That is when x becomes 3 and y is 2, you have to find the total acceleration. So you have to put the value here. So acceleration in the x direction will be equal to u, that is t square plus 3y into, what is the value of du by dx? Du by dx is 0 plus v is 3t plus 3x into du by dy. Du by dy is equal to 3 and plus du by dt, which is equal to 4. Okay, now you have to put this acceleration as 3 comma 2, 3 2, and you have to put the time as t. Time is equal to 2. So if you put the value, you will be getting this value as 3 into 2, 6 plus 9 plus 4. 6 plus 9 into 3 plus 4. That is 49. So acceleration in the x direction will be equal to 49 units. Similarly, you have to find the acceleration in the y direction. Just put all the values. Will be getting acceleration in the y direction, which will be equal to how much? That will come out to be 33 units. That will be 33. So you have found the acceleration in the x direction, y direction. You just have to do this. It will be 49 square plus 33 square ka root. That will be giving you 59. Okay. So you'll be getting 59. Okay, for this question. Next question from fluid kinematics. In force vortex flow, fluid mass rotates due to conservation of angular momentum. Velocity profile is inversely proportional to radius in force vortex flow. Every particle of the flow has same angular velocity, or p by rho g minus v square by 2g plus z is equal to constant. So this is a question. Please tell me the answer for this question quickly. Come on, everyone. Okay, so today we are having very less number of students for this session. I don't know why. The last session was so good, and I don't know why the number of students are so less for this session. Please share this session, guys, to your friends and to those who are preparing for GATE exam. Yes, come on, everyone, tell me. What is the answer for this question? The answer will be option C and D, because these two statements are for the free vortex flow. These are the statement for free vortex flow. Okay, and for force vortex flow, only these two statements are correct, that every particle of the flow has same angular velocity, and p by rho g minus v square by 2g plus z is equal to constant. Okay, so this is the statement for force vortex flow. Next question. Incorrect statement among the following is, what is the incorrect statement among the following? Tell me the answer for this question. Eulerian concept in fluid mechanics is for particular single fluid particles. Steady and uniform has no convective and local acceleration. Lagrangian concept is only for a section. Yes. What is the right answer? Clear. Tell me, everyone. Incorrect statement. What is the incorrect statement among the following? I think this question is little bit, I think, incomplete. This is incomplete question. We'll see that tomorrow. This incomplete question. There's some problem in the question here. Although the incomplete is Eulerian concept is used for, this is not correct. This is one answer. Steady and uniform has no convective and no local acceleration. Is this statement correct or not? Tell me. This statement is correct. Lagrangian concept is for a particular section. No, it is not for a section. So the right answer will be option A and C. Option D, there is a mistake here. I don't know what is the right option D. Okay. Next question. Let's study about the fluid dynamics. Let's revise the fluid dynamics. Sir, how minus v square by 2g? 1 second. Oh yeah, here that will be p by rho g plus v square by 2g plus z is equal to constant. This will be the equation. Okay, for force vortex flow, the Bernoulli equation will be satisfied. Okay, that is P by rho g plus V square by 2g plus Z is equal to constant. Clear? Now let us revise the concept of the equation of motion for fluid flow. Let us talk about fluid dynamics. In fluid dynamics, we study the forces acting over the fluid. What are the forces which act over the fluid we are going to study. Now, equation of motion for the fluid flow, there are different equation of motion, but if we talk about in fluid dynamics, we study the forces acting on a moving fluid. Okay, in fluid dynamics we study the forces acting on a moving fluid. So there are different types of forces that we study. We have gravity force, pressure force, viscous force, turbulent force, compressibility force. So my dear students, if the compressibility force is neglected, okay, so we can simply say that from equation of motion for the fluid flow, we can simply say that by Newton's law of motion, the net force in any direction is equal to mass into acceleration. Now, in case of Reynolds equation of motion, when we write Reynolds equation of motion, the compressibility force is neglected. When we write Navier-Stokes equation of motion, the turbulent force is neglected. So Navier-Stokes equation of motion will be having the force as pressure force, gravity force, and viscous force only. Okay, these are the only three forces in the Navier-Stokes equation. While in Reynolds equation of motion, will be having the forces pressure force, gravity force, viscous force, and turbulent force. These are the four forces in the Reynolds equation of motion. While in Euler equation of motion, we only consider two forces, pressure force and gravity force. Why this is important? Because this Euler's equation of motion is very important. I am going to tell you the direct relation of Euler's equation of motion, because it considers only two forces, that is pressure force and gravity forces are considered. Only pressure and gravity forces are considered in the Euler equation of motion, and so the equation of motion is simple, that is dp by rho plus vdv plus gdz is equal to 0. If you integrate the Euler equation of motion, you will be getting the Bernoulli equation. But in this Euler equation of motion, you have to apply one assumption, that is steady flow. We have to also use this assumption of steady flow to get this equation of Euler equation of motion. If you integrate this Euler equation of motion, after integrating and taking the assumption as incompressible, if we take density as constant, if we take incompressible also, in that situation you will be getting this equation, that is P by rho plus V square by 2 plus Gz is equal to constant, and you will be getting the Bernoulli equation. Okay, so you will be getting this equation, this is the Bernoulli equation. If you divide by G, you will be getting P by rho G plus V square by 2G plus Z is equal to constant. This is the Bernoulli equation. Alright, now my dear students, so we get the Bernoulli equation from Euler equation of motion, that is for sure. So my dear students, in Bernoulli equation we have to use some assumption. These are non-viscous. The fluid should be non-viscous. It should be steady flow. It should be incompressible. It should be ideal fluid, and it should be irrotational. These are the assumptions that we use in the Bernoulli equation. Okay. Now in this Bernoulli equation we have got that P by rho G plus V square by 2G plus Z is equal to constant. This is the Bernoulli equation we have got. In this Bernoulli equation, this term P by rho G plus Z, this is also called as piezometric head. Piezometric head. What is piezometric head? It is equal to sum of the pressure head plus potential head. The sum of pressure head, this is pressure energy per unit weight. This is also called pressure energy per unit weight, or per unit specific weight or weight. This is the potential energy per unit weight. This is the kinetic energy per unit head, or it is also called as pressure head plus, one second. There's some problem in my pen. Hi Sai Madhav, very good evening. Welcome to the session. So my pen is not working. Let me just wait. Just wait for 1 second. Let me just check. The pen is not working. It is having some issue here. Okay, so just wait for 1 second. All right. So this term is called as piezometric head. This is the sum of pressure head. P by rho g is also called as pressure head. It is called pressure head. Okay. And V square by 2g is also called as kinetic head or dynamic head. It is kinetic energy per unit weight, kinetic head or dynamic head. And Z is called as potential head. Okay, the sum of these three head, or we can say energy, is constant. Okay, this is the Bernoulli equation. Bernoulli equation is basically also called as energy equation for the fluid. Okay, so now for the ideal fluid, if the flow is taking place, let us say the flow is taking place in a pipe, and we have to apply the Bernoulli equation in two different sections. Let us section 1 and this is section 2. Okay, if we have to apply the Bernoulli equation across the section in a pipe, two section in a pipe, 1 and 2, then this will be the Bernoulli equation for an ideal fluid. Okay, but if it is a real fluid, will be also having head losses. The head losses will also be added here. What are these head losses? I will discuss with these head losses with you. Don't worry. What are these head losses and that we consider in the Bernoulli equation? Clear, everyone? This is our equation of Bernoulli equation for a real fluid. This is the equation for ideal fluid. Now let us talk about the application of Bernoulli equation. The application of Bernoulli equation is Venturi meter. Venturi meter basically is a device. It is a device to measure the discharge. Device to measure discharge or flow rate. Okay, discharge or flow rate. The device used to measure discharge or flow rate is called as Venturi meter. And this Venturi meter will be having inside the pipe for measuring the discharge. For inside the pipe section, will be using this converging diverging section, which is also called as Venturi meter. Okay, it is nothing but it is made of a converging diverging type nozzle section. Okay, this is a converging section in which the velocity will increase and area will decrease. As the area will decrease, the velocity will increase, and in this diverging section, what will happen? The pressure will increase. Okay, so this Venturi meter is basically made of this converging and diverging section, which is fitted inside the pipe. The main purpose is to measure the discharge. Okay, so in the Venturi meter for horizontal pipe, we can simply say that whenever it will be a horizontal pipe, the potential head will be constant. In that condition, the Bernoulli equation will be reduced to P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Yes, this lecture will include the hydraulic portion also. So if it is a horizontal pipe, then Z1 will be Z2. In that condition, this will get cancelled out for horizontal pipe. So in that situation, this P2 by P1 by P2, P1 minus P2 by, what is this W? W is equal to specific weight. This is equal to rho g. This is specific weight. Okay. So this P1 minus P2 by rho g will be equal to V2 square minus V1 square by 2g, or we can simply say that this quantity P1 minus P2 by rho g is also called as H. It is also called as pressure head. It is also called pressure head. So pressure head difference is also equal to P1 minus P2 by rho g for horizontal pipe. But if it is an inclined pipe, then we cannot neglect the value of Z1 and Z2 in the case of inclined pipe. So in that situation, this Z1 and Z2 will also be there. So this is the piezometric head difference. In that situation, the H will be equal to piezometric head difference. But if it is a horizontal pipe, the H will be equal to pressure head difference. Okay. Now, for finding the discharge from Venturi meter, this will be the formula for discharge of the Venturi meter, where A1 will be the area of this section of the pipe at the entrance of the pipe, and A2 will be the section area of the just after the converging section, the area will be A2. Okay, so that is how you will be finding the value of the discharge from the Venturi meter. This is the formula for discharge. So this is the formula for the theoretical discharge, while actual discharge of the Venturi meter will be equal to coefficient of discharge into the theoretical discharge. So this is how you will be getting the value of the actual discharge from the Venturi meter. So this is the formula. Now how you can calculate the value of H? This H given in this equation of the discharge from the Venturi meter, this H can be calculated because for measuring the discharge from the Venturi meter, we have to find the value of H. and this H is also can be measured with the help of a manometer, YouTube manometer installed in the Venturi meter section. So basically, as you know that in this section, this is a converging section of the Venturi meter, okay, and this is a diverging section of the Venturi meter. So there will be some pressure difference between both the section, right? Now that pressure difference can be measured with the help of a Venturi, with the help of a YouTube manometer. That deflection of the pressure or the manometric deflection. This is the manometric deflection. The manometric deflection can be measured due to the pressure difference. There will be some manometric deflection or deflection in the pressure, the level of the liquid inside the manometer, which can be measured with this formula. Now there are two cases here. There are two cases here, my dear students. If the manometric fluid flowing inside the manometer is having higher specific gravity than the specific gravity of the flowing fluid inside the pipe, okay, if the value of the specific gravity of the manometric fluid is greater than the S, then the value of H will be this. But if the value of the manometric fluid is less than the value of the specific gravity of the fluid flowing inside the pipe, then this will be the formula of H. So H will become X. X is the manometric deflection into 1 minus of SM. SM is the specific gravity of the manometric fluid. Okay. Inclined Venturi meter, we neglect the kinetic head. Specific gravity of manometric fluid. Okay. And S is the specific gravity of the liquid flowing inside the pipe. So this is how you will be measuring the value of H. By just finding the value of H, you can just put the value and you can find the value of discharge from Venturi meter. Next is the coefficient of discharge. It is equal to the ratio of the actual discharge by theoretical discharge. So I have already told you about this. There are some important points regarding the Venturi meter. That is, the diameter of the diverging section is equal to 1 by 3 to 1 by 2 of the diameter of the converging section. This is an important relation. Also, the angle of convergence is around 20 to 22 degree, and also the angle of divergence must be below 7 degree to avoid the boundary layer separation. To avoid boundary layer separation in the Venturi meter, in the diverging portion, the angle of divergence, this divergence angle beta, should be less than 7 degree, so that the boundary layer separation can be avoided in the Venturi meter. Okay. Next device for measuring the discharge is orifice meter. Orifice meter is also a device used for measuring the discharge, but this is little bit less costly. It is less costly as compared to Venturi meter. Why? Because in orifice meter, we simply use an orifice plate inside the pipe section in order to measure the discharge. Okay. So in compared to Venturi meter, it is basically less costly because we just require a plate with a hole inside that plate. That is also called an orifice meter. So it basically simply consists of a flat plate inserted inside the pipe like this. Okay, so this is a flat plate. It is just having some circular cavity, which is also called orifice. Okay. All right. Now, because of this small orifice, which is also, we think that this is the theoretical minimum area. We think that this is the theoretical minimum area, but this is not the theoretical minimum area, because just after the orifice will be having an area which will be having a section which is also called vena contracta section, which is also called the minimum area section. Minimum area section after the orifice. So that area or that section after the orifice meter, which is having very minimum area, that is called as vena contracta. Now, coefficient of discharge for orifice meter lies between 0.68 to 0.74. It is very important. While for the coefficient of discharge for Venturi meter lies between 0.97 to 0.98. Okay. So coefficient of discharge is more for the Venturi meter as compared to orifice meter. See, more is the coefficient of discharge, more correct value of more correct will be the discharge you will be getting from a particular device. So because it is having more value of coefficient of discharge, Venturi meter will give more accurate reading of discharge as compared to orifice meter, because it is having less value of coefficient of discharge. That means, because why it is having less value of discharge, coefficient of discharge, because it is having more losses. Because it is having more losses, that is why this coefficient of discharge will be less. Okay. Now, in the case of orifice meter, there is a term called coefficient of contraction. This is called coefficient of contraction. It is equal to ratio of actual minimum area divided by theoretical minimum area. We think that in the orifice meter, the minimum area is the area of the orifice, but actually it is not that, because just after the orifice, we'll be having a section where the area reduces to minimum. That section is called vena contracta section, which is section 2 here. Okay, so at section 2 actually we are getting the minimum area. Okay, so the ratio of this actual minimum area divided by theoretical minimum area is called coefficient of contraction. Now there is also a relation between coefficient of contraction and discharge. I will tell you later on. Now this is the formula for discharge through the orifice meter. It is equal to coefficient of discharge into A1 into A0, where A0 is the area of the orifice and A1 is the area of the pipe. This is how you find the value of discharge through the orifice meter. And H you can find by the same relation we have used for the Venturi meter. Okay. Now loss in case of orifice meter are high because the convergence of area is sudden and hence leading to losses. Actually, what happens in the case of an orifice meter, because in a Venturi meter, this section of convergence comes gradually, not suddenly. So because of that, the losses in the case of the sudden losses, the loss due to sudden contraction will be less in the Venturi meter. So because losses will be less in Venturi meter, the coefficient of discharge value will be more. But in the case of orifice meter, because the convergence comes very suddenly inside the pipe, will be having this very minimum area. We'll be getting very minimum area in the pipe just suddenly. So because of that, there will be more losses in the orifice meter, and because of that, the coefficient of discharge of the orifice meter will be less than the coefficient of discharge of Venturi meter. Okay, clear everyone? This is very important. Next, Pitot tube. Pitot tube is basically a 90-degree bent glass tube which is used to measure the velocity of the fluid flow. So basically, if you have to measure the velocity of the fluid in the pipe or in the open channel we don't study in the fluid, mechanical engineers don't study about the open channel, but for a civil engineer, definitely open channel flow is important. So in the open channel flow application, you can find the velocity through Pitot tube. You just simply need to install this Pitot tube inside an open channel and you can get the velocity. So velocity you can get from this relation, it is equal to under root 2 GH, where H is equal to stagnation head minus static head. The stagnation head is the total head. What is the meaning of stagnation? It is the point where the velocity suddenly reduces to 0. Okay. So difference of the stagnation head minus static head will give you the value of H, and from here you can find the velocity from open channel. But we don't study open channel. For mechanical engineers, generally the question comes from velocity of the fluid in the pipe. Okay, so we have to generally find the velocity in the pipe. So you can find it by using this relation. Velocity can be found by using this relation only from Venturi for Pitot tube in a flow through pipe, where H is equal to this. This is how you find the value of H. H is equal to X, which is the manometric deflection into the manometric specific gravity divided by specific gravity of the liquid flowing in the pipe minus 1. Okay, so this is how you will be finding the value of H. This is how you will be getting the velocity. Okay, now let us solve one question. Let us solve few questions from the concept of fluid dynamics, and then we'll be quickly starting the topic of laminar flow through pipe and plate. So because we have to hurry up, we have got very less time left. So be quick, guys. Tell me the answer for this question. A Pitot tube having CV. See, one more important thing, that this velocity you get from Pitot tube, it is the theoretical velocity. It is a theoretical velocity, but actual velocity is actually equal to CV under root 2GH. What is this CV? CV is also called as coefficient of velocity. It is also called coefficient of velocity. And the coefficient of velocity is equal to, it is having some value of 0.972 around 0.98. It is having this value, coefficient of velocity. Okay, so this is how you will be getting the actual velocity from Pitot tube. So you have to remember this thing. Now, my dear, solve this question quickly. Hi, Bunny Kaushik. Very good evening. Welcome to the session. Those who are joining me for this session, also please like the session. Today, the number of students are so less. I think I have to think about this thing, because we are providing you this session, and I can see some of the students are, although you have got the session yesterday, and I can understand that it is the last time that most of you are revising for GATE 2021. So definitely this session is useful for everyone. But today strength of the students make me think that should really we should give this session to you or not, because today the strength is very less. I think that some of the students think that we can watch the recorded session. That is why the students are not joining the session. Maybe that is the issue. Okay. Yes, what is the answer? Tell me everyone. Shrikant Bodhi is giving 19.80. The velocity of the water from Pitot tube velocity will be equal to C under root CV under root 2GH. Very simple question. C is given, the coefficient of velocity C is given 1. So it is simply equal to under root 2GH. What is the differential manometric reading? That is 20 mm. So H is equal to X times of SM by S minus 1. Right? This is the formula for finding the H. This X is the manometric deflection given here as 20 mm. Okay. Gaurav Bajpai has given 2.076 as the answer. Come on everyone. Tell me the answer for this question quickly. Be quick guys. Gaurav Bajpai has given 2.076. Hi Gaurav, how are you dear? कैसे हैं आप? So Gaurav is one of the Vision student. I think you were in the Vision batch. So how are you Gaurav? I hope your preparation is going good for GATE exam. Relative density is also given. The relative density is given as 12. And we can say the manometric fluid is the fluid inside the pipe is actually water, so S is equal to 1, right? So it is very simple. H will be equal to 20 into 10 power minus 3 into 12 by 1 minus 1, that is 11 into 20 into 10 power minus 3. So you will be getting the value of H from there. Just put the value of H, you will be getting, just put the value of H you will be getting here, just put it here, you will be getting velocity as 2.07 meter per second. 2.076, yeah, that is the answer you will be getting. Very good, Dinesh, Shrikant, Shivani. Shrikant has got 0.626. Yeah, thank you so much, Gaurav. Now, what is the answer for this question? Which of the following equation assumes the fluid to be non-viscous for the analysis of the fluid motion? Euler's equation, Navier-Stokes equation, Bernoulli equation, or Huygens-Poiseuille equation? Yes. Yeah, the reason why I'm giving you this session, why we are basically I'm taking this session and at this point of time is that right now this is the time for revision of the entire subjects, and after that you have to solve the mock test. That is the time left before the GATE exam now. So that is why I'm basically giving this revision session for each subject. But today your the strength of the class is very less. I don't understand why. Yes, which of the following assumes fluid to be non-viscous? Non-viscous means it does not consider the viscosity. Yes, it is it Euler equation of motion, Navier-Stokes equation, Bernoulli equation, or Huygens-Poiseuille equation? Yes, Appan Raj has given AC, Dinesh A, Prateek A, Shrikant is saying Euler. Yes, tell me everyone, what is the answer for this question? Yes, come on everyone, tell me. A, C both. A, C both. Okay. It is Euler equation, Bernoulli equation. That is for sure. What about Huygens-Poiseuille equation? Is it for only for laminar flow? It is for turbulent flow also. Yes. Is Huygens-Poiseuille equation for laminar flow or only for turbulent flow? See, A and C are 100% correct. Navier-Stokes equation contains the pressure force, gravity force, and viscous force. All these three forces are considered in the Navier-Stokes equation. So obviously that cannot be the answer. Euler equation consider only pressure force and gravity force. It does not consider the viscous force. Bernoulli equation have been derived from the Euler equation. So A and C are 100% correct. What about Huygens-Poiseuille equation? Huygens-Poiseuille equation basically you study for the viscous flow in the pipe, right? So that is option D is also not the answer. The answer is option A and C. Next question. A cylindrical vessel of height 8 meter contains a liquid up to a height of 5 meter as shown in the figure. So there is a cylindrical vessel and we are having two sections. This is section 2, this is section 1 we have considered here. Okay, so the water is basically up to height of 5 meter. It is containing liquid up to height of 5 meter. The top surface of the liquid is exposed to gauge pressure of 55 kilopascal. So here the pressure is given 55 kilopascal. An orifice of diameter 800 mm is located on the bottom surface of the vessel. Find the discharge from the orifice if coefficient of discharge is 0.65. Yes, the Hagen-Poiseuille equation is only for the laminar flow. Exactly. Tell me the answer for this question quickly. Yes, this is again a question from the fluid dynamics. Everyone quickly answer the question. We have to revise the laminar flow through pipe and plate after this. Then we have to revise the turbulent flow. Then we have to revise boundary layer. Then we have to revise dimensional analysis. And then we have to revise the hydraulic turbines. So we have a lot of things to revise. So hurry up guys. We don't have much time, my dear students. Come on, hurry up. And guys, those who have joined me recently, please do not forget to like the session and share the session also. Okay? Come on everyone, be quick. Tell me the answer for this question quickly. So we are having two sections here. Already two sections are given here. So we just have to find the value of discharge. How can we find the value of discharge? We have to apply the Bernoulli quotient. Definitely, let me give you a hint. You have to apply the Bernoulli quotient between 1 and 2 section. So if you apply the Bernoulli quotient, it will be P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square over 2g plus Z2. This is section 1. We can say this is section 1, this is section 2. Okay, now apply the Bernoulli quotient, you will get the answer very easily. Come on, tell me everyone. The pressure P1 is given as, this is the value of P1 is 55 kilopascal. So this is 55 into 10 power 3 Pascal divided by 10 power 3 into 9.81 plus V1 square by 2g. Velocity is given at this section 1. Is velocity given in section 1 or not? Yes, tell me. Will there be any velocity at section 1? At section 1, at this point, it is a free surface. So the liquid is only present up to this point. Above it, it is only air. So we can also say it is a free surface. And at the free surface, the velocity will be 0. So velocity will be 0 at this point. V1 will be 0. What will be Z1? Z1 will be equal to 5. Next is P2. What will be the value of P2? Yes, because this is the gauge pressure given here. This is the gauge pressure. And this section is open to the atmosphere. This is the orifice. It is open. So at this point, P2 will be having 0 gauge pressure. It will not be having any pressure. So you will be taking 0 gauge pressure here. Plus velocity. Velocity at this section will be what? It will be having some velocity obviously at the orifice, V square 2g plus 0. So from here you can find the value of V2. V2 will be getting from here. That will be 14.42 meter per second. Okay, you will be getting 14.42 meter per second as the velocity at this section 2. So if you have got the velocity, you can find the discharge very easily because the diameter is given here 800 mm. Diameter is equal to 800 mm, that is 0.8 meter. Okay, so you can find the discharge, that is pi by 4 into d2 square into v2. You'll be getting the discharge very easily from here. So are you getting the answer, everyone? So you'll be getting discharge, but that discharge will come out to be 7.2511 meter cube per second. But this discharge will be the theoretical discharge. Because we have given the coefficient of discharge, the actual discharge will be equal to the coefficient of discharge into theoretical discharge. That will be 0.65 into 7.2511. So you will be getting the value of the actual discharge, which will be coming out 4.713. You will be getting 4.713 meter cube per second. So the answer will be option B for this question. The reason why we have not taken the actual pressure, because they have given here gauge pressure. Okay, because they have given gauge pressure, so we have to take the reading in gauge pressure, because here there will be no gauge pressure. We are not having any gauge installed here, so we'll be taking gauge pressure 0 here. Why we have to take it, convert into atmospheric pressure? See, if we have to take here P2 as atmospheric pressure, if you have to take it as atmospheric pressure, we can do that. There is no harm. But then we have to find P1 in terms of absolute pressure by adding atmospheric pressure to this. Because we are not adding atmospheric pressure here, we are taking gauge pressure. So here also we'll be taking this P2 as 0. Because the gauge pressure is 0 and the section 2, at section 2. Next question, water flow through a pipeline having 4 different diameter at 4 section is shown in the figure. The correct sequence of the station number in the decreasing order of pressure is. What is, you can see the water is flowing. The water is flowing in different section. This is section 1, this is section 2, this is 3 and 4. So you have to tell what is the correct sequence of the station. This is station 1, this is station 2, 3 and 4. What is the correct section? Come on, tell me, what is the correct section, correct order of the decreasing order of the pressure in this different section? Come on, tell me. Yes. How Z2 is equal to 0? Z2 is equal to 0 because we are starting our measurement from this point. We are taking this our reference. This is our reference level. Okay, so this measurement of Z1 definitely is equal to Z1 is equal to 5 meter, right? Because this is section 1, but Z2 we are starting from 2 point only. So that is why Z2 will be equal to, the value of Z2 will be equal to 0. Come on, tell me what is the answer for this question. Come on, everyone, be quick. Water flow through a pipeline having 4 different diameter. The diameter are different. Here the diameter is 2D. Here it is 1.5D. It is equal to 4D. Here it is equal to D here. Now, a very important thing is that the mass flow rate in each section will be same. Because the mass flow rate in the each section is same. Now, you can tell me, when it is very obvious that mass flow rate in the each section is same. So you know that because water is incompressible fluid, we can say the product of area into volume is equal to constant. Area into velocity is equal to constant. That is, the discharge is equal to constant in each section. Okay. Now, because discharge is constant in each section, you know that velocity, if velocity will be increasing, if area is decreasing, if area is increasing, velocity will be decreasing, right? So in that, the section in which will be having more velocity, that will be having, or which will be having more area, will be having less velocity and more pressure, right? So that area, that section which is having more diameter will be having, yes, that section which is having more diameter will be having, so section having highest diameter will be having highest pressure, right? So that section will be having highest pressure. So here the diameter highest is for section 3, then it is for section 1, then it is for section 2, then 4. So the answer will be option D for here. So pressure is inversely proportional to velocity, exactly. So we can say that as the area will be increasing, the velocity will be decreasing and pressure will be increasing. So that section which is having the highest area will be having the highest pressure. Okay, so that is how, this is a very good question. This question can come in the exam. It is a very good question with a very good concept. Okay, so let's move on to the next concept. Let us discuss about the viscous flow through pipe and plate, or laminar flow through pipe and plate. Okay, now what is a laminar flow? I have already talked about the laminar flow, that it is that flow which is considered to be a highly viscous flow. A flow which is governed by high viscosity and low velocity is called laminar flow. So in the laminar flow in the pipe, we can simply say that if the Reynolds number is less than or equal to 2000, it is considered to be laminar flow. Okay, so laminar flow, it is a flow which is characterized to be having more viscosity, a flow which is having more viscosity or highly viscous flow, or highly viscous flow, or we can simply say that laminar flow is also called as viscous flow. Okay, so this is how the fluid particles will be flowing in the laminar flow, like this. This is how the fluid particles will be flowing in the laminar flow, perfectly streamlined. Okay, now my dear students, there is a concept of fully developed flow. What is the meaning of fully developed flow? When the fluid start to enter inside the pipe or any section. So when the fluid start to enter in the pipe, initially the fluid velocity profile is flat profile. But as the fluid proceed inside the pipe, as the flow proceed inside the pipe, what happens? Suddenly the velocity profile becomes more stable. And now there comes a point after which the velocity profile, the variation of the velocity profile totally stops and the velocity profile becomes constant. So that section after which the velocity profile becomes constant, that section is called as fully developed region, where velocity profile does not vary. Hi Kuldeep, very good evening. Kuldeep dear, very good evening. Where the velocity profile does not vary, that section is called as the fully developed area or fully developed region. Okay, so that fully developed region will be having a fully developed velocity profile, after which there will be no variation of the velocity profile. Okay, so that is a very important consideration of the fully developed flow. Now, very important relation is that for the laminar flow through pipe, the shear stress is given by tau is equal to minus of del P by del X R by 2. So this is how the shear stress vary for the flow through pipe. Now this shear stress will be having, this R is also called as local radius. Local radius. Okay, so tau, that is the shear stress, vary as minus del P by del X and R by 2. So my dear students, this shear stress will be maximum at the wall. At the wall this shear stress will be maximum, and at the center of the pipe the shear stress will be 0. Well, that is when R will be 0, the shear stress will be 0. When R will be equal to the radius of the pipe, then tau will become maximum. And in that condition, the maximum shear stress will be equal to minus of del P by del X R by 2. That is the maximum shear stress in the viscous flow through pipe. Okay. Next is the velocity distribution in the laminar flow through pipe. This is how you will be getting the velocity distribution. See, velocity distribution for laminar flow through pipe is a parabolic. It is having a parabolic velocity distribution. Okay, it is very, very important. The velocity distribution for laminar flow is the parabolic velocity distribution. And what is the shear stress? Shear stress distribution is linear. It is 0 at the center and it will be increasing around as the flow will proceed near the wall of the pipe, the shear stress will become maximum. At the center of the pipe, the shear stress will be 0. Now, if we talk about the fully developed for the velocity profile in the pipe, the velocity profile will be parabolic for the laminar flow through pipe. So, velocity will be maximum at the center and it will be 0 at the wall. At the wall, the velocity will be 0. At the center, it will be maximum. This is how the velocity will be varying. It will be having parabolic velocity distribution. Now, if this is the velocity distribution you will be getting for laminar flow through pipe, if you apply the boundary condition, for this fluid developed laminar flow through pipe, you will be getting this velocity relation. Now, this velocity relation is called, this is the local velocity. It is equal to minus 1 by 4 mu del P over del X into R square 1 minus R square over R square. This is a local velocity. This is a local velocity which varies with some local radius. That is called local velocity. Local velocity is that velocity which varies in a particular region of the flow through pipe. Okay, that is called local velocity, which varies with respect to distance or with respect to a local radius. In that, this term is called as maximum velocity. It is called maximum velocity. You can say that local velocity is equal to maximum velocity into 1 minus R square by R square. This is a very important relation. It is, you have to remember. Okay. Now, if we talk about the discharge in the pipe, discharge for fully developed laminar flow in the pipe is equal to this. This is the formula for discharge. Total discharge, it is equal to minus pi by 128 into mu del P by del X of D power 4. Okay, that is the formula for discharge for laminar flow through pipe. The total discharge. Now, total discharge is also equal to area of the pipe into the average velocity of the flow through pipe. So my dear students, this velocity in the flow through pipe is equal to minus 1 by 4 mu del P by del X R square. This is also called maximum velocity. But for finding the value of Reynolds number, we use the average velocity. We use the average velocity. For finding the discharge also we use the average velocity. So we have to find what is the average velocity for the flow through pipe. Okay. So for finding the average velocity, we have to equate this total discharge to this formula. It is equal to pi into d square by 4 into the average velocity. If you equate it, you will be getting this average velocity is equal to minus 1 by 8 mu del P by del X of R square. This is the average velocity you will be getting. Now there is a relation between the average and maximum velocity, that is average velocity is equal to half of maximum velocity for the laminar flow through pipe. For laminar flow through pipe, the average velocity is equal to half of the maximum velocity. Okay. Now next is the pressure drop in the laminar flow through pipe. How you can find the pressure drop for laminar flow through pipe? The pressure drop is equal to 32 mu VL by d square. This is a derivation for the pressure drop. Because average velocity is equal to half of maximum velocity, the maximum velocity will be 2 times the average velocity. From here you can simply say that maximum velocity is equal to this. If you integrate it, you will be getting this relation. P1 minus P2, which is the pressure drop, is equal to 32 mu VL by d square. This is a pressure drop, but this pressure drop is only for fully developed laminar flow through pipe. For fully developed laminar flow through pipe, this is the formula for pressure drop. Now comes the very important equation. This is a formula for fully developed laminar flow in the pipe, formula for pressure drop. But because we know that if we are having an horizontal pipe and we are having 2 sections in the horizontal pipe, let us say this is section 1, this is section 2. Okay, if you apply the Bernoulli equation for this horizontal pipe, so this is the Bernoulli equation you will be getting for a real fluid. Let us say we are having a real fluid, it will be having some head losses. So this is the Bernoulli equation you will be getting. Z1 will be equal to Z2 because it is a horizontal pipe, right? So from here we will simply say that also because area A1 is equal to A2, because the diameter is same, we can say diameter is same, so area will be same, so velocity will be same here. In that situation, this will also get cancelled out. So head loss will be equal to P1 minus P2 by rho g. Now comes a very important part. We have just seen that pressure drop is equal to 32 mu VL by d square, where V is the average velocity, L is the length, and mu is the dynamic viscosity, D is the diameter of the pipe. Now this, if you put the value 32 mu VL by d square into rho g, this will give you the head loss. But this is a formula for the head loss for laminar flow through pipe. This is very important. This is a formula for head loss for laminar flow through pipe. Okay, and this equation 32 mu VL by rho g d square, this is the formula for head loss for laminar flow through pipe. Okay, so this is a very important relation. This is also called as Hagen-Poiseuille equation. Hagen-Poiseuille equation. Okay, so sometimes in an exam they will give you to find the value of discharge to find the head loss for laminar flow through pipe. If it is a pipe flow and if you have found the Reynolds number, it is coming out to be less than 2000, then definitely you can apply this formula. If Reynolds number is less than equal to 2000 and if it is a flow through pipe, you can apply this formula for head loss. It is equal to 32 mu VL by rho g d square. Okay, clear everyone? So that is a very important formula. Is it clear to everyone? Now we have just seen that head loss is equal to 32 mu VL by rho g d square. That is the head loss we have seen. But we also know that we can find the head loss. We can also find the head loss by using this relation FLV square by 2GD. This is also formula for finding the major head loss due to friction, where F is the friction factor. If you equate these two head loss, you will be getting friction factor is equal to 64 by Reynolds number. But this is a formula for friction factor. See, I am in a bit hurry because we are revising the things. Okay, otherwise I can, please just tell me, have you understood? Okay, I can see 3 dislikes in my session. Every day 3 people dislike the session. I don't know why. I think these 3 people hate me, or because maybe you are not liking my content. See, there is nothing to hate, my dear. I am just teaching you for revision of GATE 2021. If you don't like the session, just simply leave the session, my dear. Don't need to dislike here, my dear. Okay, don't need to demotivate me, because I am not going to get demotivated. I will be teaching you what is my purpose. I have to teach you, so I'll be doing that. Okay, no matter whether you like or dislike the session. So my dear, we are getting the friction factor. This is the formula for friction factor in terms of Reynolds number for laminar flow. Okay, so if it is a laminar flow through pipe, if it is laminar flow through pipe, we can simply find the value of the friction factor by using this relation 64 by Reynolds number, simply. So my dear students, one more thing, friction coefficient is equal to 16 by Reynolds number. Okay, what is friction coefficient? This is the fanning factor. The fanning factor or friction coefficient. Friction coefficient or fanning factor is equal to 16 by Reynolds number. It is also for fully developed laminar flow through pipe. Okay, so one more important thing, that two correction factors that we use for the flow through laminar flow through pipe, laminar or turbulent flow through pipe, that is called momentum correction factor and kinetic energy correction factor. So why we use this correction factor? The simple thing is that because in the laminar flow or in the turbulent flow, there is a difference between the local velocity and the maximum velocity, because the velocity continuously varies. In the turbulent flow, this variation, the velocity is very less. Why? Because in turbulent flow, the mixing of the fluid takes place. So because of that, the velocity variation is very less in the turbulent flow. Because the velocity variation is very less in the turbulent flow, the momentum correction factor, which is equal to this is a formula for momentum correction factor. It is equal to 1 by AB square integration of 0 to R of mu square dA. Okay, where u is the local velocity, and this is the average velocity. Okay, this is the formula for momentum correction factor. This is the formula for kinetic energy correction factor. But directly, if we talk about the what is the value of this correction factor, the kinetic energy correction factor alpha is equal to 2 for laminar flow and 1.33 for turbulent flow. Momentum correction factor beta is equal to 1.33 for laminar flow and 1.2 for turbulent flow. You must be thinking, why is the value of alpha and beta, that is correction factor for laminar flow, are more? Why they are more? Because there is a very high difference of the velocity between local and average velocity, has a very high variation in the laminar flow. Why? Because there is less mixing of the fluid particles in laminar flow, but in turbulent flow, due to intermixing of the fluid, the velocity variation is less. Due to intermixing of the fluid, the velocity variation is less, and because of that, the value of correction factor are less for the turbulent flow as compared to laminar flow. Next, we are going to study the laminar flow between two fixed parallel plates. When the laminar flow is taking place between two parallel fixed plates, in that condition, you are getting this equation del tau by del y is equal to del p by del x. This is an important relation, that the shear stress del tau by del y is equal to del p by del x. This you get from the derivation. Okay, by applying the force balance equation, you will be getting this relation for the laminar flow between two parallel fixed plates. Okay, now what is the velocity distribution for laminar flow through parallel fixed plates? So velocity variation, you will be getting this. This is a velocity variation. Local velocity is equal to, so if we are having two parallel fixed plates, both the plates are fixed and both the plates are situated at a distance of b from each other, that is the thickness between the two plates. Okay, now we can say that the width of the plate is unity. Width of plate, we can take it as 1 or unity. We can say the plate are having very less width. We can take it as unity. So this is the local velocity of the laminar flow through between two parallel fixed plates. Between two parallel fixed plates, the local velocity is equal to 1 by 2 mu of minus del p by del x of by minus y square, where y is called the distance from pipe wall. Distance from the pipe wall. Okay, so or we can say distance from the plate. This is the plate. So this y will be defined as the distance from the plate. Whether you say distance from the upper plate or lower plate, the y is the distance from the plate. Okay. So we have got this relation of the local velocity for the laminar flow between two parallel fixed plates. This is a very important relation because I will be using this relation for some purpose. Don't worry. Okay, I will tell you. I will be explaining about the Couette flow also. Okay, so in that I will need this relation. Velocity varies parabolically in the laminar flow between two parallel fixed plates also. Between two parallel fixed plates also, the velocity variation will be parabolic like this. Okay, so velocity will be maximum at the center and it will be 0 and the here. Why it will be 0 and the pipe wall and the near or we can say why the velocity is 0 near the surface of the plate. It is 0 because of no slip condition. It is 0 because of no slip condition, because here the plates are fixed. They are fixed plates. Both the plates are fixed, and because of that the velocity will be 0 at this particular point. Okay, so maximum velocity will be getting at the center, and it is a parabolic velocity distribution. Parabolic velocity distribution is there. Same like for laminar flow between parallel in the pipe, same applies for laminar flow between two parallel fixed plates. Okay, now the velocity variation, local velocity was this. Now this velocity will be maximum when y will be b by 2. When this distance from the pipe wall will become b by 2, and then at that condition the velocity will become maximum. Okay, so if you put y is equal to b by 2 in this relation, you will be getting the maximum velocity. The maximum velocity will be equal to this. This is the maximum velocity for laminar flow between two parallel fixed plates. Now total discharge, this is a total discharge for laminar flow between two parallel fixed plates. Total discharge. Now the total discharge will be equal to area into velocity. The area is equal to b into 1. B is the distance between the two parallel fixed plates, that is b. Okay, and the width is unity here. So this is the total area into velocity, average velocity. From here you will be getting, this is the average velocity. This is the average velocity. This is the maximum velocity. So what is the relation we will be getting between average and maximum velocity for laminar flow between plates? The average velocity is equal to 2 by 3 of maximum velocity. This is an important relation for laminar flow between two parallel fixed plates. Two parallel fixed plates, the average velocity is equal to 2 by 3 of maximum velocity. For laminar flow through pipe, the average velocity was equal to half of maximum velocity, but for plate it is equal to 2 by 3 of maximum velocity. Like we have found the pressure difference for laminar flow in a pipe, similarly the pressure difference for laminar flow between two parallel fixed plates is equal to 12 into mu into L. What is this L? And L is the total length of the plate by B square. B is the thickness between the plate or the distance between the two plates, that is B or thickness. This is B here. The length of the plate is L, mu V. V is the average velocity. This is the pressure difference. You can use this formula for finding the pressure difference for laminar flow between two parallel fixed plates. Now, shear stress. The shear stress for laminar flow through pipe was equal to minus del P by del X of R by 2, right? But here it will be equal to minus del P by del X of B by 2. Okay, this is the formula for shear stress distribution between two parallel fixed plates, where B, remember what is B? B is the distance between the or thickness between the two fixed plates. Now, important thing I have to tell you about the Couette flow. This is a special case of Couette flow which I have to tell you. For that I need one blank slide. Let me just enter one blank slide here. I need one blank slide at this point. Okay, where I need a blank slide. Yes. So I just need a blank slide here. So we have seen the laminar flow between two parallel fixed plates. But there is one more important special case which is called Couette flow. What is Couette flow? It is a special case in which the upper plate is moving with some velocity. It is having some velocity, and the lower plate is fixed. Okay, or if the flow is laminar flow is taking place between two plates, one plate is fixed. This plate is fixed, let us say, and the other plate is moving. This plate is moving with a velocity v. Everything is same for the laminar flow between two in this Couette flow condition. Only one thing is different, that is we have got this velocity distribution. This was the velocity distribution. Sorry, this was the velocity distribution here. Okay, so in this velocity distribution 1 by 2 mu, u was equal to 1 by 2 mu del P by del X of y square plus C1y plus C2. Okay, so how can you solve this Couette flow problem? For this, your boundary condition will be different. What will be the boundary condition? The boundary condition will be at y is equal to 0, your u will be 0, at y is equal to b, your u will be equal to v. That is, at y is equal to b, when y will become equal to b, this local velocity will become equal to this velocity of the moving plate. So this will be the boundary condition that will be changed. If you apply the upper boundary condition, y is equal to 0, u is equal to 0, you will be getting c2 is equal to 0. If you apply the lower boundary condition, that is u becomes v, that will be equal to 1 by 2 mu del p by del x of b square plus c1 of b. Okay, so from here you can find the value of c1. c1 will be equal to that will be equal to v minus 1 by 2 mu del p by del x b square. Okay, divide by b. So this will be simply equal to v by b minus 1 by 2 mu del p by del x of b. Okay, so this will be the value of c1. If you put the value of c1 in this equation, you will be getting the local velocity is equal to 1 by 2 mu del p by del x of y square plus v by b of y minus 1 by 2 mu of del p by del x of by. Now, this is the equation you get for the local velocity for the Couette flow. But in the Couette flow, we are having a very special case for simple or plain Couette flow. What is simple or plain Couette flow? Simple or plain Couette flow is when the pressure gradient becomes 0. The condition when pressure gradient becomes 0, at that condition this will become 0, this will become 0. In that, the local velocity will be equal to v into y by b. This will become the local velocity. This is the equation of plain Couette flow. Equation of plain Couette flow. Plain or simple Couette flow. So you have to remember this equation. Plain Couette flow, simple Couette flow take place when the pressure gradient become 0. Okay. When there is no pressure gradient, we can say that we can get the condition of simple or plain Couette flow. Now let us solve few problems on the laminar flow through pipe and plate quickly. Then we are going to understand the turbulent flow. So hurry up guys, we have to quickly cover the laminar flow through pipe, then turbulent flow, then boundary layer, then dimensional analysis. Okay, clear everyone? Have you understood this Couette flow? Now let us quickly solve some questions on laminar flow through pipe and plate. Hurry up. An oil of viscosity 10 poise flows between two parallel fixed plates. So there are two parallel fixed plates, and between two parallel fixed plates we are having some oil which is having viscosity. Viscosity is equal to 10 poise. Okay, that is the CGS unit of giving CGS unit of viscosity is given. Now these plates are having a distance of 40 mm. The plates are situated at a distance of 40 mm. The average velocity is given. The average velocity is also given as 0.5 meter per second. You have to find the magnitude of pressure drop in a length of 1.2 meter. Yes, quickly tell me the answer for this question. What is the actual? See, I will tell you the relation of actual velocity to average velocity. Don't worry. अभी turbulent flow पे हम आए नहीं है साई माधव. Just have some patience. I will come to turbulent flow. There I will tell you what is the relation of actual velocity to average velocity. Don't worry. In turbulent flow, there are so many correlations that you are going to get confused which relation we have to use for solving the question. Okay, so don't worry. Have patience. You will get everything. Okay, so what is the pressure drop? Pressure drop for laminar flow between two parallel fixed plates. What is the pressure drop relation? Tell me the answer for this question quickly. It is equal to 12 mu VL by B square. So that will be equal to simply 12 into mu. Mu is equal to 10 poise. Now 1 poise is equal to 1 by 10 Pascal second. We have to convert into Pascal second. So that will be equal to what? It will be equal to how much? That will be equal to 1. This will be equal to 1 Pascal second. That will be 1 into V, that is 0.5 into L, that is 1.2 divided by 40 mm, that is 14 to 10 power minus 3 whole square. Solve it, you will be getting the answer as 4.5 kilopascal. Okay, game हुआ unit में, so the answer will be option C. Clear everyone? Next question, a fluid of density 0.840 gram per centimeter cube. So density is given as 0.840 gram per centimeter cube inside a pipe of diameter 15 centimeter and length of 20 mm at 126 kg per second. Then velocity of the fluid at r is equal to 3 centimeter is this much. This is a MSQ question. This is a MSQ question. So quickly solve the question. Tell me the answer, everyone. Yes, hurry up. Hurry up, everyone. Be quick. So you have to find the velocity of the fluid at r is equal to 3 centimeter. That is, you have to find the local velocity. It is equal to minus 1 by 4 mu del p by del x of r square minus r square. This is the formula. Okay, so from here you will be getting the local velocity. Local velocity you will be have to find at r is equal to 3 centimeter. 3 centimeter, that means 0.03 meter. The total radius diameter of the pipe is given. Diameter is 15 centimeter. So radius is equal to 7.5 centimeter. Okay. At 126 kg per second. The mass flow rate is given 126 kg per second. Yes, come on everyone, tell me the answer. Yes. What will be the density? Density is equal to 0.840. 0.840 gram per centimeter cube. It will be equal to 840 kg per meter cube. If we convert it, it will become 840 kg per meter cube. Okay. Now the flow rate, mass flow rate is equal to 126 kg per second. Right? Now mass flow rate is equal to rho into Q. So Q will be equal to mass flow rate divided by density. So you will be getting 126 divided by 840. You will be getting discharge. Discharge will be equal to 0.15 meter cube per second. So from here you have got the discharge. Now discharge is equal to area into velocity. So total discharge is equal to area into velocity. Average velocity basically. So we can find the average velocity from here. So you can simply say that area is equal to pi by 4 into d square. D is 0.15 square into average velocity. Discharge is 0.15. So from here you will be getting the average velocity. What is the average velocity? Tell me. The average velocity you will be getting as, yes, you will be getting the average discharge. The average, we can simply say that the average velocity will be getting from here 8.49. You will be getting average velocity as 8.49 directly from here, meter per second. Because you have to find the average velocity, this is equal to maximum velocity of r square minus r square. So average velocity is equal to maximum velocity by 2. So maximum velocity will be equal to 2 times of average velocity. So you will be getting here average maximum velocity, just put the value, you will be getting the local velocity. So what is the right answer for this question? Yes. What is the right answer for this question? The right answer is option A, B and D. A, B and D. All the 3 options are correct. The right answer is option A, B and D. So option A you will be getting, if you put maximum velocity from here, you have found the average velocity 8.49. Maximum velocity you will be getting 2 into 8.49. You just put the value here. That will be 2 into 8.49. How much you will be getting? 2 into 8.49. It will be 16.98. Okay, so you'll be getting 16.98 as the maximum velocity. Just put the here, you will be getting this value as 14.26 meter per second. R is equal to 7.5 centimeter. Just put it into meter. Okay, this is 0.03 meter. Next is shear stress. Shear stress is equal to minus del p by del x at r by 2. At r is equal to 0.04 by 2. You will be getting the value of shear stress. That will be equal to 0.24 Newton per meter square. How you will find del P by del X? Because mu maximum is equal to minus 1 by 4 mu del P by del X of R square. So from here mu is also given. The viscosity is given or not in this question? Yes. Okay, viscosity is not given. So no problem, you can find the value of del P by del X. Del P by del X you can find by using the relation. I think viscosity has to be given. Viscosity given है कि नहीं given? In this question, viscosity has to be given. Viscosity is missing here. Viscosity is equal to 1 centipoise. Sorry guys, the viscosity is viscosity you can take 1 centipoise. It is equal to 1 centipoise. That is missing in the question. Or it is equal to 0.001 Pascal second. So viscosity was missing here. That is 0.0. You can take as 1 centipoise or 0.001 Pascal second. Okay. So viscosity was not given. You can take viscosity as this. If you put the value of viscosity here, you will be getting the answer very easily. Maximum velocity you have found 16.98, and viscosity is also given. R is also given. So you will be getting the pressure difference. So pressure gradient you will be getting dP by dx. dP by dx will be equal to how much? You can find the value of dP by dx, that will come out to be 12.072. 12.072. If you know the value of mu is equal to 0.001 Pascal second. Okay. Yeah, there was a mistake. Viscosity was missing here. That was mistake. Viscosity has to be given. So viscosity will be 0.001 second. 0.001 Pascal second. That will be the viscosity. So will be getting the pressure gradient. Are you getting the pressure gradient, everyone? Tell me. Are you getting the pressure gradient from there? Now you can just put the value. You will be getting the value of pressure at that condition. So shear stress will be equal to minus of del P by del X. At R is equal to 0.04 by 2. You will be getting the answer as 0.24. That will be 0.24 Pascal. Okay. Now the last one is pressure drop. Average velocity is not correct. So pressure drop is equal to, how can you find the pressure drop? Pressure drop is equal to 32 mu into V average into L by D square. Because everything is given, average velocity you already found, everything is given. You can simply find the pressure drop from here. The pressure drop will be equal to 241.5 Newton per meter square. Are you getting everything? So that is a very simple question, good question. This type of question can be asked in the GATE exam. I mean, as the MSQ question. Okay. So sorry about this thing that I did not notice that viscosity was not given. That is why you were facing this issue. So I'm really sorry about this. Next time I will make sure that all the values are given in the question. Okay. Next question: a steady flow of water takes place through a pipe of 100 mm internal diameter and 10 meter length. The average velocity of the flow is 5 meter per second, and the wall shear stress is 250 Newton per meter square. The pressure drop for the given length you have to find. So you have to find the pressure drop for the flow through pipe, that is equal to 32 mu VL by D square. You know the formula, they have given the average velocity is also given. The wall shear stress is given 250 Newton per meter square. So you have to find the value of the pressure drop. Quickly answer the question, everyone. Yes. How can you solve this question? Quickly tell me. So I have forgot to tell you that there is a direct formula for the wall shear stress. Wall shear stress can also be found by using the direct formula, and that direct formula I think you should know. It will be definitely very much helpful for solving some of the questions. The wall shear stress is also equal to rho f v square by 8. This is a direct formula for the wall shear stress. The wall shear stress is equal to density into friction factor into average velocity divided by average velocity square by 8. This is a formula. So this formula is also very, very important. Okay. So wall shear stress is given in the question. So how can we solve this question? As you know that the pressure drop per unit length, is equal to pressure drop by rho g. P by rho g is equal to head loss, that is equal to FLV square by 2GT. Okay, so we can simply say that the pressure drop, the pressure drop will be equal to FLV square by 2GT into rho g. Okay, so this will get cancelled out, G will get cancelled out. So you can get that pressure drop is equal to FLV square into rho divided by 2D. So F is the friction factor, L is the value of length of the pipe, V is the average velocity. Okay, now wall shear stress is given, this is 250. So we can simply say that the wall shear stress is equal to 250. So rho FV square is equal to 250 into 8. Okay, so simply we can say that if rho FV square is equal to 250 into 8, you can find it from here. So pressure drop was equal to what? Rho FV square into L by 2D. So you can simply say that this will be equal to 250 into 8 into L. L is equal to what? The length of the pipe is 10 meter. 10 divided by 2 into internal diameter is equal to 100 mm, that is 0.1. So you can simply find the pressure drop from here, that will giving the answer. That will give equal, the answer will be 1 into 10 power 5 Newton per, it will give you 1 into 10 power 5 Newton per meter square. Are you getting the answer, everyone? So you have to remember this formula, it is a very important formula for wall shear stress, it is equal to rho FV square by 8. Okay, or we can simply say that the pressure drop will be equal to 8 into tau naught L, 8 into wall shear stress divided by L by D square. If you use this formula, then also you'll be getting the direct answer. So you can say pressure drop is equal to 8 into 250 into L. L is equal to what? The length of the pipe is equal to 10 divided by D square, that is 0.1 whole square. If you just solve it, you will be getting the answer. Are you getting the answer, everyone? Yes? Are you getting the answer, everyone? Sorry, that will be 2D. Sorry, 2D. 2 into D. 2 into 0.1. So you'll be getting the answer is 10 power 5 Newton per meter square. So this is a direct formula. You can remember the pressure drop. The pressure drop can also be found by 8 into tau naught wall shear stress into L divided by 2 into D. This is a formula you can remember for finding the pressure drop. Okay, sometimes you can use this formula also. It is an important formula. Okay, if wall shear stress is given, length of the pipe is given, and diameter is given, you can use this formula: 8 into wall shear stress into L by 2 into D. D is the diameter. Now next we are going to study about the losses through the pipe. So losses through the pipe, generally if we talk about losses through the pipe, we have to study mainly two losses. One is called as major loss and another is called as minor losses. So major and minor losses are the two losses that we study. Major loss and minor losses. So जब भी आपके पाइप के अंदर फ्लो होता है, then we'll be having these two types of losses, which is called major and minor losses. Major loss can be found by using two formula. One is called as Darcy-Weisbach equation. Darcy-Weisbach equation. Another is the Chassis formula. So Darcy-Weisbach equation is a very famous equation for finding the major head loss due to friction. The major losses basically take place due to friction. When the flow will take place inside the pipe, there will be some losses, head loss due to friction. Darcy-Weisbach equation is used to find the major head loss due to friction, and that is equal to, major head loss due to friction is equal to FLV square by 2GT, where F is the friction factor here. Okay, now one more formula for head loss due to friction is that because this friction factor is equal to 4 times of friction coefficient. Okay, so you can also write this formula as 4 into F dash LV square by 2GD. This is a formula for head loss due to friction, but in terms of the friction coefficient. So F dash is called friction coefficient. Sometimes in your exam they will be giving you friction coefficient, not friction factor. And most of the time they will be giving you the friction coefficient to remember this formula. You have to remember that what they have given. If they have given friction factor, you have to use this formula. If they have given friction coefficient, you have to use this formula. Clear everyone? So you have to be very much careful that what is being given in the exam. Okay. So they can ask you to find the head loss due to friction. You can use both of this formula. One more formula is that because the discharge is equal to area into velocity, right? And area is equal to pi by 4 d square for the pipe, right? So we can also write the velocity is equal to 4 into q by pi d square. If you put the value of v in this equation, so you will be getting one more formula for head loss due to friction, that is equal to FLQ square by 12.1 d power 5. Approximately you can take it as FLQ square by 12 d power 5. Now this formula for a major head loss will be used specially for solving for pipe in series and parallel connection. So for solving the problems of compounding in the pipe, we'll be using this formula for head loss, FLQ square by 12 d power 5. It is a very important formula. Okay. Next formula is for equation is Chazy's equation. Chazy's equation is very simple. It is used to find V is equal to C under root M into I. This is a Chazy's equation. C is called Chazy's constant, and M is called as hydraulic mean depth, that is equal to D by 4 for pipe. For pipe flow it is equal to simply D by 4, or M is equal to area divided by wetted perimeter. Area divided by wetted perimeter, or that perimeter of the pipe which is actually that area of the pipe which is totally wetted by the fluid, that is called wetted perimeter. Okay, so basically the area is equal to pi d by 4 d square, and this is pi d, so you'll be getting this value as d by 4 for the pipe. Okay, so this is hydraulic mean depth or hydraulic mean radius. Okay, and I is called as hydraulic flow, which is equal to HF divided by L. If you put the value, you'll be getting C, V is equal to C under root D by 4 into HF by L, where HF is the major head loss due to friction. So by using this formula, you can find the major head loss due to friction. Okay, clear everyone? So this is how you'll be finding the value of head loss due to friction by Chazy's formula. This is D by 4 into HF by L. Okay. Now another type of losses are basically minor losses. The minor losses are basically sudden expansion loss, sudden contraction loss, exit loss, entry loss, bend losses. So these are the different types of minor losses. But these losses carry only 5% of the loss, because these losses only take place when there is a sudden expansion while flow take place in a pipe. When suddenly the diameter of the pipe has suddenly increased, or suddenly the diameter of the pipe has decreased. Okay, so these losses only take place when there is sudden reduction or increment of the area, or suddenly there is an entry to a particular area or particular section of the pipe, or there is an exit from the pipe. Then these losses will take place. Okay, so sudden expansion loss basically take place due to formation of the eddies. When sudden expansion takes place due to formation of turbulent eddies, there is a loss that is called sudden expansion loss. This sudden expansion loss is given by V1 minus V2 whole square by 2g. If we take V1 square by 2g common, this will be 1 minus V2 by V1 whole square, that is equal to this. This is a formula for sudden expansion loss. Sudden contraction loss basically is actually equal to the loss due to sudden expansion, because when sudden contraction takes place, actually we get an area which is a minimum area, or which is a vena contracta area. So when we have to find a sudden contraction loss, actually we have to find a sudden expansion loss between the vena contracta and the actual output from the pipe. When actual output, when the flow actually comes out from the pipe. So between these two sections, we have to apply the formula of sudden expansion. Okay, so sudden expansion, if you apply the formula, you'll be getting this equation. In this equation, this particular value is equal to K, and this K is equal to 1 by Cc minus 1 whole square. This Cc is called coefficient of contraction. You already know about what is coefficient of contraction. It is equal to actual minimum area divided by theoretical minimum area. This is equal to A2 by AC. Okay, actual divided by theoretical. Theoretical is this, actual is this. Okay, so if the value of Cc is not given, you can take value of K as 5. So you can say that sudden contraction loss is also equal to 0.5 of V2 square. V2 is the velocity at the exit of the pipe near the after the vena contractor section, that is V2. So this is a direct formula for finding the loss due to sudden contraction. Then entry loss. Entry loss is nothing but when entry takes place. Entry is definitely from a large reservoir to a very small pipe. So when entry takes place, it is actually the sudden contraction which takes place. It is sudden contraction because when the flow actually enters from a big tank into a very small pipe, it is actually the sudden contraction. So entry loss is equal to sudden contraction loss, which is equal to 0.5 of V square. V is the velocity of the fluid in the pipe. So this is the formula for entry loss. And exit loss is nothing but it is actually the loss due to sudden expansion, because when the flow actually comes out from the pipe, it goes to very large area. So exit loss is equal to sudden expansion loss. Actually it is actually equal to sudden expansion to a very large reservoir or tank. Okay, so this exit loss is directly equal to V square by 2G. You can simply use that formula. Okay, now we are having bend losses. Bend loss is equal to K V square by 2G, where K is called bending coefficient. That value is also will be given in the question. Bend, there are different types of bend. It can be bend at 45 degree, it can be bend at 90 degree. Generally the bends are like this. This is how the bend will be. Okay, so why we use bend in the power plant, in some industries we use the bends, because if we have to make the flow take place from a very large, very small section, then we are not able to use a very long pipe. In that condition, we have to use pipe bend. Okay, so when we use a pipe bend, these pipe bend are nothing but these are bent pipe which are at some particular angle like 45 or 90 degree. Okay, so when the flow takes place from this pipe bend, there is some loss that is called bend loss, which is equal to Kv square by 2G. Next is pipe in series and parallel connection. See, we do this series and parallel connection. Why? If we have to do some transportation of some fluid, whether we have to transport water, whether we have to transport any fluid, we have to transport oil or anything, then we have to connect the pipe either in series connection or parallel connection. Series connection is always done in order to increase the head loss. Okay, because when we connect pipe in series, our main purpose is to transport a fluid to a very long distance. But when we do that, actually our head loss will increase. Our head loss will increase when you do series connection, but discharge will remain same. Discharge will remain same during the series connection. So when we connect the pipe in series connection, the head loss will get added up and discharge will remain same. That is a very important thing. While in the series connection, there is a direct formula. This formula we get is called Dupit's formula. According to Dupit's formula, the equivalent length of the pipe in series connection, you can combine all the different pipes of pipe into an equivalent pipe. Let us say it is having some equivalent length of LE and equivalent diameter of DE. Okay, so all the pipes combine to form one single pipe which is having equivalent length of LE and equivalent diameter of D. So we can simply say that this equation is called Dupit formula for finding the equivalent length or equivalent diameter of a pipe in series. So this formula will be using for pipe in series connection. Okay, so for pipe in series connection, you can simply say that all the head loss will get added up. Okay, so this is the formula of head loss I have already discussed with you. So from here you can find the equivalent diameter or equivalent length of the pipe. So equivalent length of the pipe is equal to all the length of the pipe will get added up, and equivalent diameter you can find by using this relation. Next is pipe in parallel connection. When we connect the pipe in parallel connection, the main purpose is to increase the discharge. If we have to increase the discharge from the pipe, we have to connect the pipe in parallel connection. Okay, so when the pipes are connected in parallel connection, basically what happens, the discharge is increased but head loss is same. The head loss becomes same, but the discharge increases. So this will be the condition which happens in the parallel connection. When the pipes are connected in parallel connection, this will happen. Okay. So the head loss will get discharge will get added up, and the head loss will be same. For let us say we are having n pipes which are connected in parallel connection. So this is the condition you will be getting for pipes in parallel connection. This is the equivalent diameter power 5 divided by equivalent length is equal to this. This is the formula you will be getting. Okay, clear everyone? So power transmission through the pipe. If you have to find what is the amount of power to be transmitted, which we can transmit from the pipe, that power is equal to theoretical power is equal to rho g q h, where h is the total head, q is the discharge, rho is the density, g is the acceleration due to gravity. But actual power will be less as expected from theoretical power, because due to the friction head loss, due to friction the actual power will be less. That we can transmit from the pipe. So this is the actual power. It is equal to rho g q h minus hf. Now this HF, you know, it is the head loss due to friction. Head loss due to friction. Okay. So the efficiency of the power transmission is equal to actual power divided by theoretical power, and you will be getting this value for efficiency. If we have to find the condition of maximum efficiency, then maximum efficiency will happen when the head loss due to friction will be equal to 1/3 of the total head. When the head loss due to friction will become 1/3 of the total head, you will be getting actual maximum efficiency, and that maximum efficiency of power transmission is equal to 66.67%. Okay. Now let us solve some problems on this topic of losses through the pipe. Okay, let us solve some questions. Okay, so let us quickly solve some questions. This is the first question. Two identical pipe of length L, diameter D, and friction factor F are connected in series between two reservoirs. The size of the pipe of the length L and of same friction factor F equivalent to our pipeline is. So basically you have to find the equivalent diameter for pipe in series connection. So there are two identical pipe. They are having same length, diameter, and friction factor F. Okay, you have to find what is the value of the equivalent diameter in this connection. Come on everyone, quickly answer the question. So in this condition, we can simply say that L1 is equal to L2 is equal to L, and D1 is equal to D2 is equal to D. Okay, so we can also use this Dipit's equation, equivalent length divided by D power 5 is equal to L1 D1 power 5 plus L2 D2 power 5. You can use this equation also. So in this question, they have given everything is same, friction factor also same. Okay, come on everyone, tell me. So you can simply say this will be L over D power 5 is equal to L by D power 5 plus L by D power 5. Okay, clear? This will be equal to 12 divided by D power 5. Okay, L power D power 5. This will get cancelled out. So you can simply say that equivalent diameter will be equal to diameter power 5 is equal to D power 5 divided by 2. So you can simulate equivalent diameter is equal to D. Let us say the initial diameter is equal to D. They have given D here, so let us say this is D divided by a second. Yes, tell me what is the answer for this question. Come on, tell me. So they have taken the value of small d. Okay, let us take it as small d, no problem. Okay, no problem. We can take it as small d, no problem. Tell me what is the answer. D1 is equal to D2 is equal to D. Okay, so that will be D power 5, D1 power 5, D2 power 5. This will be D power 5, D power 5. Okay, that will be L by D power 5 is equal to basically This will be equal to 2L by d power 5. This will get cancelled out. We can simply say that this equivalent diameter power 5 is equal to d power 5 divided by 2. So d will be equal to d divided by 2 power 1 by 5. So we'll be getting this value equal to how much? Yes, 0.87 d. Yes, this will be equal to 0.87 of d. Okay, simple. Next question. Two pipes of length 2500 meter each and diameter 80 centimeter and 60 centimeter respectively are connected in parallel. Okay, so there are two pipes which are having equivalent length. So L1 is equal to L2 is equal to 2500 meter and the diameter D1 is equal to 80 centimeter and D2 is equal to 60 centimeter. They are connected in parallel connection. The coefficient of friction for each pipe, friction factor is also given same, that is 0.006. The total discharge is equal to 250 liter per second, that is 0.25 meter cube per second. You have to find the rate of flow in the larger pipe. Okay, so as you know that in the flow through parallel pipe, the discharge is equal to discharge gets added up. Okay, so you have to find the discharge in the larger pipe. Larger pipe means in this pipe which is having more diameter. So you have to find the value of Q1 in this question. Quickly answer the question, everyone. So it is a pipe in parallel connection. So obviously the head loss will be same. The head loss will be same in this type of in this connection. Okay. So what is the head loss formula? The head loss is FLQ square by 12 d power 5. So head loss will be same. Q1 F1 L1 D1 F2 L2 Q2 power 5 divided by 12 D2 power 5. So this will get cancelled out. F1 F2 will get cancelled out. L1 L2 will get cancelled out. We can simply say that Q1 square divided by D1 power 5 is equal to Q2 square Q2 power 5 divided by Q2 square divided by D2 power 5. Okay. So you can simply find the relation between, because the diameter is given, you can simply say that your Q1 you can find here. Your Q2 will be equal to D2 by D1 power 5 by 2 into Q1. So Q2 will be getting from here. Alright. So how much will be the value of Q2? Q2 will be equal to 0.487 of Q1. If you put the value of D2 and D1 in this equation, you will be getting Q2 is equal to 0.487 of Q1. Okay. So the total discharge is equal to 0.25 is equal to Q1 plus 0.487 of Q1. So from here you will be getting the value of Q1. Q1 will be equal to how much? Tell me. Q1 will be equal to 0.168. Yes. Q1 will be equal to 0.168 meter cube per second, or it is equal to 168 liter per second. That is, the answer will be option B. Very good. Very good. Deepak Kumar Shah, Kumari Mahesh, Jarad, Gaurav Vajpayee, Arnav Manna. Very good evening. Very good. You all have given the right answer for this question. Next question, the head loss due to friction in a pipe of diameter 200 mm and length 30 meter through which the water is flowing at a velocity of 4 meter per second. The constant of Chailly's formula is 60. So you have to find the head loss due to friction. Quickly answer the question. The Chailly's constant is also given in this question. Yes, hurry up everyone. Quickly hurry up. The head loss due to friction you have to find in this. Chailly's constant is already given in the question. So you know that the velocity is equal to the velocity is equal to c under root mi. This is the formula of Cheggy's equation. The velocity is given 4, Cheggy's constant is given 60, m is equal to d by 4 already I told you for the pipe, okay, and I is equal to hf by L. So you can simply use this formula and you can get the answer. Vivek Jial, yes, you can ask the question. What is your question? Quickly ask the question. Yes, come on everyone, quickly tell me the answer for this question. The diameter is also given 200 mm. Diameter is equal to 200 mm or 0.2 meter. Okay, the length is equal to 30 meter in this question. The head loss you can easily find from here. What is the value of head loss? Hi Muzibal Haq, very good evening. Welcome to the session. So m will be equal to d by 4. D by 4 you can put the value of d. This will be, you will be getting the head loss from here. So head loss will be equal to what? Head loss due to friction will be 2.66 meter. Okay, so the answer will be option C in this question. Yes, very good. Shivani, Gaurav, Deepak Kumar Shah, very good. You all have given the right answer. Good. Next question: a liquid of viscosity 7 poise is flowing in a horizontal pipe. Is flowing in a horizontal pipe of diameter 120 mm at the rate of 12 liter per second. If the kinematic viscosity of the fluid is 8 stoke, find the power in kilowatt required per kilometer to overcome the viscous resistance to flow the liquid through the pipe. You have to give the answer up to 2 decimal places. Very good, very good. Those who have given the answer for this question: Shivani, Gaurav, Abhay Kumar. Good, good, very good. Deepak Kumar Shah. Hi Mozibul Haq, very good evening. Welcome to the session. So everyone, those who have joined me for this session, please quickly like the session, share the session also. Yes, those who have joined me for this session right now, please like the session, share the session. A liquid of viscosity 7 poise is flowing in a horizontal pipe of diameter 120 mm at the rate of 12 liter per second. If kinematic viscosity of the fluid is 8 stoke, find the power in kilowatt required per kilometer. Yes. So firstly, you have to find, you have to check. It is a flow through a horizontal pipe. You have to check what is the Reynolds number. Reynolds number you have to find here. In a multi-layer fluid, oil and water body, 0.5 volume inside water and 0.5 inside the oil. Water is of 1000 kg per meter cube. Find oil density. Vivek Joel, you have to use the Archimedes principle. The total buoyant force will be equal to the weight of body. So you have to use this relation. I have solved one question in the last lecture. I have solved one question based on this concept. Okay, Vivek. So you can see that concept. You can solve this question by Bernoulli question. Sorry, not Bernoulli. You have to solve by Archimedes principle. The buoyant force due to water plus buoyant force due to oil will be equal to weight of the body. So you have to apply this concept. Okay. So 0.55 volume, that is buoyant force due to water, will be equal to rho into G into V. Okay. Density of water into G into volume of water. What is the volume of water? 0.55 of V. What is the volume of that other fluid? It is equal to that is density of the oil into G into volume. It is 0.45 into V. That will be equal to density of the body into G into V. Okay, so from here you can easily find the value of density of the, you can find the density of the oil. Yeah, you can find the density of the oil from here. Okay, is it clear everyone? Hi Shiva Tribe, very good evening. Welcome to the session. बहुत late हो गए आज आप. Okay, clear? Vivek Joel. So you have to use this concept for solving that question. Reynolds number you have to find, that will be equal to rho v d by mu. Okay, you can use this formula. The value of density is given here or not? The rate of flow is given. Kinematic viscosity is also given. So if kinematic viscosity is given, you can also use this relation. Vd by mu also you can use. Okay, because the liquid is not mentioned, whether it is liquid, is water or something else. Okay, so very good evening Shiva Tribe, very good evening. Yes, Gaurav Ajpai has got the answer. 0.0198 kilowatt. So the right answer will be 19.786. 19.786 kilowatt will be the right answer. Let's see how to solve the question. So let me tell you the solution for this question. In this question, you have to find the value of the Reynolds number. I have told you Reynolds number you have to find. Why you have to find Reynolds number? Because it's a flow through pipe. So we have to check whether it is a laminar flow or turbulent flow, because power is equal to rho G Q H F. HF is equal to 32 mu VL divided by rho G D square. But this formula only be used for laminar flow. So we have to check whether it is a laminar flow or not. Okay. So because it is a flow through pipe, we have to check whether it is a laminar flow or not. Velocity is given in this question. Now there is discharge is given in this question. Yeah, discharge is given. Q is equal to 12 liter per second. Okay, or it is equal to 12 into 10 power minus 3 meter per cube per second. So you can find the discharge is given, diameter is given, discharge is equal to area into velocity. So from here you can find the velocity. Velocity will be getting from here. That is 1.06 meter per second. If you put the velocity here, you can get 1.06 into 0.12 divided by mu. That is 8 stroke. 1 stroke is equal to 10 power minus 4 meter square per second. That will be 8 into 10 power minus 4 meter square per second. If you put the value, you will get the Reynolds number. Reynolds number will be equal to 159.12. Because it is a laminar flow, you can put the value of head loss as this. That will be simply equal to rho G Q into 32 mu VL divided by rho G D square. So this rho G will get cancelled out. It will be simply equal to Q into 32 mu VL by D square. Just simply simply put all the values. Discharge is given to you 32 into mu. Mu is the given viscosity 7 poise. Okay, or it is equal to 0.7 Pascal second. V is also given. You have found 1.06. Length of the pipe is also given or not. Okay, you have to find the power per kilometer. Okay, so it is given per kilometer, so you don't have to find this. It is P by L. So you can find the answer very easily from here. Got it? Have we got 19.786 kilowatt? Just put all the values, will be getting the answer. Okay. Next question. Quickly answer the question. Which of the following pairs are not correctly matched regarding the minor losses? Sudden expansion loss is equal to this V1 square V1 minus V2 whole square by 2G. Sudden contraction loss is equal to this, bend loss is this, or loss of head exit of the pipe is equal to coefficient of contraction into V square by 2G. Hi Thakur Shivam Rajput, very good evening, welcome to the session. Those who have joined me for this session, please do not forget to like the session, share the session, and अगर आपने चैनल को सब्सक्राइब नहीं किया है तो जल्दी से कर लीजिए क्विकली. Hi, good evening everyone, my dear students. Those who have just joined the session, I have just completed the fluid dynamics, laminar flow through pipe and plate, and losses through the pipe. Now the topics we are going to discuss are turbulent flow, dimensional analysis, and boundary layer, and then hydraulic turbines also. Yes, what is the right answer for this question? Come on, tell me. You have to do the match the following. I'm perfectly fine, Shivam. B and D. Sudden expansion loss is equal to A, correct? This is not correctly matched. Okay, which of the following is not correctly matched? Sorry. Not correctly matched. So this is not correctly matched. B. And D, loss of head exit of pipe is not equal to this. It is simply equal to V square by 2G. So these two are not correctly matched. So the right answer is option B and D. Okay. Next, turbulent flow. So when we are going to study the turbulent flow, yes, B and D is the right answer for this question. Very good, Abhay Kumar. B and D both are not correct. Okay. So what is turbulent flow? Laminar flow, just opposite to laminar flow, in a turbulent flow, the fluid particles move at very high velocity. So turbulent flow, it is also called a very random flow, where the fluid particles move at random velocity in a zigzag manner. So because the velocity is very variable in the turbulent flow, due to intermixing, the velocity will be fluctuating with space and time coordinates. So there will be fluctuation of the velocity. So because of that, the For analysis of the turbulent flow, we'll be using two combinations. One is the average component, one will be the fluctuating components. When we were analyzing the laminar flow through pipe and plate, we were only considering about one thing, average velocity. But here we have to consider two components. One is the average velocity, one is the fluctuating velocity. Two velocity will be there. So any parameter in the turbulent flow will be composed of two components, average component plus fluctuating components. Like velocity will be composed of fluctuating velocity plus average velocity. So a flow is said to be turbulent in a pipe if the Reynolds number is greater than 4000, and in laminar flow through plate, if Reynolds number is greater than 10 power 7, it is called turbulent flow. Okay. Now in the turbulent flow, there are very important things that I have to tell you. In turbulent flow, the shear stress is a combination of laminar shear stress and turbulent shear stress. So total shear stress in the case of the total shear stress in the turbulent flow is the sum of shear stress due to laminar flow and turbulent flow. Shear stress in the laminar flow or viscous flow is equal to mu times of du by dy, which can be easily found by Newton's law of viscosity. But what about the shear stress in the turbulent flow? That is a question. Now shear stress in the turbulent flow can be found by using this equation by Boussinesq hypothesis. According to Boussinesq, the shear stress in the turbulent flow is equal to eta times of du by dy, where u is the average velocity and eta is the eddy viscosity. Okay, so this is the total shear stress. Total shear stress in the turbulent flow is the sum of the shear stress due to laminar flow plus the shear stress in the turbulent flow. In the turbulent flow, the shear stress is equal to eta times of du by dy, where eta is the eddy viscosity. Now, the question was that this eddy viscosity is very difficult to obtain. One more thing. So one hypothesis was this Boussinesq hypothesis. He gave the shear stress is equal to this, but this hypothesis it was also not exactly clear to give you the value of the shear stress in turbulent flow. Then Reynolds gave one more hypothesis, Reynolds hypothesis. So according to Reynolds, he says that the turbulent shear stress is equal to rho times of u dash into v dash. So the total turbulent shear stress is equal to this rho into u dash into v dash, where u dash and v dash are the fluctuating component of velocity. But there was another problem with the Reynolds hypothesis, that these two components are fluctuating components. They cannot be measured very easily. So we have to convert these fluctuating components into some measurable quantity. So solution to this problem was given by Prandtl. Prandtl gave a mixing length model, and according to Prandtl, he says that u dash is equal to L times of, L times of du by dy, and v dash, these two fluctuating component of velocity, he said that it is equal to u times du by del y, and v dash is also equal to L times of du by dy. So he says that this fluctuating component of the hypothesis means assumptions. The meaning of hypothesis is the assumptions, okay, that have been taken by different scientists, the assumptions that have been taken for the study. Okay, so according to Prandtl, he says that the fluctuating component of velocity, if we have to convert that fluctuating component of velocity into some measurable quantities, you can use this relation. U dash is equal to L du by dy and v dash is equal to L du by dy. If you put this value, you can say that the total shear stress in the turbulent flow is equal to rho times of L square du by dy whole square. So this has been given by Prandtl. This is a result of the Prandtl, and Prandtl result is greatly accepted. This is a Prandtl result for turbulent shear stress, where this L is called as Prandtl mixing length. It is called Prandtl mixing length, and this Prandtl mixing length is equal to K into Y, where K is equal to 0.4, that is called Karman constant. K is equal to 0.4 called Karman constant. Okay, so if you put all the values here in this equation, you can simply say that tau is equal to rho L square du by dy whole square, or du by dy whole square is equal to tau by rho L square. Okay. Now if you take a square root, you will be getting this as du by dy is equal to tau by rho 1 by ky. This tau by rho is root of tau by rho is equal to shear velocity. This is called as shear velocity in the turbulent flow. So shear velocity in the turbulent flow is equal to root of the wall shear stress divided by the density. This is the shear velocity in the turbulent flow. It is very important relation. So du by dy we have got Vs by ky, shear velocity divided by k into y. Y is the distance from the pipe wall. Y term will, wherever we will be using this y term, it means distance from pipe wall. Okay, and k is the Karman constant, its value is 0.4. So we have got the relation that du by dy in turbulent flow, du by dy is equal to Vs by ky. If you integrate this, you will be getting, because k is equal to 0.4, so you will be getting this as 2.5 of Vs by y, du by dy. So if you integrate this, du will be equal to 2.5 of Vs by y dy. If you integrate this for turbulent flow, you will be getting this relation. U will be equal to 2.5 shear velocity into log of y. If you apply the boundary condition, for turbulent flow in the pipe, y is the distance from the pipe wall. If y becomes r, u will become maximum. Okay. So my dear students, if you just put the value, if you put the boundary condition, you will be getting this final result, that maximum velocity minus local velocity is equal to 5.75 into shear velocity log base 10 r by y. This is a relation you will be getting for velocity. This is also called difference of the velocity, maximum velocity minus local velocity. This is a maximum velocity in the turbulent flow in the pipe. This is the maximum velocity and u is the local velocity. Okay. So maximum velocity and local velocity are related by this relation in the turbulent flow in the pipe, and the difference of maximum minus local velocity is called velocity defect. Sometimes they can ask you to find the velocity defect. Hi Parth Sharma, hi. Welcome to the session, Parth. Good evening, my dear. Enjoy the session. Okay. Now there are different conditions of in the turbulent flow. We have to study about a very important condition, that is the hydrodynamically smooth and rough pipes. So turbulent flow basically depends on the roughness of the pipe, because inside the pipe, because of the irregularities, because of the surface irregularities inside the pipe, the turbulent flow take place. Okay. So my dear students, because of the irregularities inside the pipe, the flow becomes turbulent. And the height of the irregularities, let us say k is the average height of the irregularities in the pipe. Okay. Which is useful, maximum local. Shiva tribe, this is the only concept, that is the turbulent flow, where all the relations are useful. Okay, here you will be studying about local velocity relation, maximum velocity relation, shear velocity relation, and average velocity relation. So here there are many types of relations you have to use for solving the questions from turbulent flow. Okay, so there is a term called thickness of laminar sublayer. This is also called thickness of laminar sublayer. In the turbulent flow region, we come across a region which is also called laminar sublayer region. Thickness of laminar sublayer, I will tell you what is the formula for that. Okay, so thickness of laminar sublayer is this delta dash, and k is the average height of the roughness or irregularities inside the pipe. Okay, now there is a very important result that we get. Okay, don't worry, but whatever formula I am going to tell you in this session, those formula are definitely going to help you for solving the question of turbulent flow. According to Nickerdays experiment, if k by delta dash is less than 0.25, or if k by delta dash is less than 0.25, that value is less than 0.25, that is called smooth boundary. If K by delta is greater than 6, it is called rough boundary. And if it lies between 0.25 to 6, it is called transition boundary. Delta dash is also called as thickness of laminar sublayer. Thickness of laminar sublayer. And that is equal to, sometimes they can ask you to find the, sometimes they can ask you to find the thickness of laminar sublayer. It is equal to 11.6 into nu is the kinematic viscosity divided by shear velocity. This is the formula for thickness of laminar sublayer. So you can use this formula. Okay. How much you earn? Part, my dear, I will tell you all this thing. How much I earn or how much I'm getting from how much salary I get. That is all the other type of question. Right now we should discuss about something technical. Let us study this. Later on I will tell you about all this, all those things. So shear velocity already I have told you it is equal to tau naught, that is the wall shear stress divided by density root of that. It is also equal to average velocity into root of f by 8. Okay, so shear velocity is equal to wall shear stress divided by rho root of that, or it is equal to average velocity into root of f by 8. This is the formula for shear velocity. This is the formula for thickness of laminar sublayer. These are very, very important relation. Now I am going to tell you more important relation. Try to focus here. Velocity distribution for turbulent flow in smooth pipe. This is the velocity distribution in terms of local velocity and shear velocity. U star I will be using for shear velocity. I will be using U star for shear velocity, U for local velocity, U bar for maximum velocity, and simply these are the different types of velocity you have to use. So my dear students, the velocity distribution for the smooth pipe, for turbulent flow in smooth pipe is equal to this. This is the velocity relation in terms of local velocity and shear velocity. It is equal to 5.75 log base 10 of U shear velocity into Y. This is shear velocity into Y by V. Okay, V is the average velocity. V is the average velocity. Okay, so this is the formula for velocity distribution for turbulent flow in smooth pipe in terms of local and shear velocity. Velocity distribution for rough pipe. This is a velocity distribution for rough pipe where K is the height of roughness. K is the height of roughness. Y is the distance from the pipe wall, and this is log base 10. This is not 10, this is log base 10. This is also the relation between local and shear velocity. This is a relation for smooth pipe. This is a relation for smooth pipe, turbulent flow through smooth pipe in terms of average velocity and shear velocity. This is a relation for rough pipe in terms of average velocity or mean velocity and shear velocity. And this is the relation for difference of the local and average velocity and shear velocity. This can be used for both rough and smooth pipe. Okay, so in turbulent flow I told you there are different types of correlation, but whatever correlation I have told you here, I have shown you here, only these correlations are important for you to remember. Okay, you just have to remember these correlations. Now let us quickly solve few problems quickly on turbulent flow so that we can move on to the next topic, which is boundary layer. Come on, hurry up guys. We have to solve, we have to understand boundary layer, then we have to understand the dimensional analysis, and then hydraulic turbines. So hurry up, be quick. We don't have much time. Today I have to complete the lecture at 8 p.m. anyhow. I cannot extend beyond 8 p.m. That is the time allotted to me today. I cannot extend beyond that. Okay. Timing is limited today. Only up to the. So let us cover how much we can. Let us cover as much as possible today. According to Prandtl mixing length theory, the turbulent shear stress tau is. Yes, Deepak Kumar Shah has given A, Gaurav Vajpayee A, Bunny Kaushik A, Shivani Rai A. Very good. The answer is right. Answer is option A. Good. Very good. Next, in a turbulent flow through a pipe of radius R, At what distance from the boundary would the local velocity be equal to mean velocity? A very good question. This question can again come in the exam. Come on, tell me the answer for this question. Very good, Vikas Yadav, Apan Raj, Shivani Rai, Bunny Kaushik. Good, good, very good. Tell me the answer for this question. You have to tell that at what condition when the local velocity will become equal to average velocity. Under that situation, what is the relation between y and r? Y and r, relation between, what is the relation between y and r? Y is the distance from the wall and the r is the radius of the pipe. See, I cannot cover Vikram anything in detail, okay? Because the reason is very simple, Vikram, because we have very less time. You will be very lucky if I am able to cover the boundary layer and dimensional analysis. Not in detail, but in whatever best possible way, because this is just a revision session. When I will come for discussion of one particular chapter, there I will discuss everything in detail. So in the qualified series in the night at 11 p.m. I will discuss about all these topics in detail. Okay, there I will be only discussing about the topics individually. Here is a revision of all the topics together. So here I cannot cover anything in detail. Okay, so the answer will be option D for this question. Very good. Shivani Rai, Deepak Kumar Shah, very good. You have given the right answer. So how can you solve this question? I have just told you one relation. This relation, my dear, you have to use this relation. The local velocity is equal to u minus u bar divided by shear velocity is equal to 5.75 log base 10 of y by r plus 3.75. So you just use this relation. You have to find this relation. You have to find this relation when local velocity becomes equal to mean velocity. So when local velocity becomes equal to mean velocity, this term will become 0. So in that situation, 5.75 log base 10 of y by r is equal to minus 3.75. If we solve it, you will be getting y by r is equal to 0.707 or y is equal to 0.707 r. Okay. Next question, a discharge of 300 liter per second of petrol where rho is equal to 680 meter cube per second and mu is equal to 2.9 10 power minus 4 pascal per second is passing through a 30 centimeter diameter pipe in smooth turbulent flow design. The friction factor of this flow is estimated to be 0.0097. Determine the maximum velocity of the flow in the pipe. 11 p.m. High 133 YCET 16. Actually 11 p.m. is the timing for qualified series that happens every day at 11 p.m. in the night. So in that qualified series I will be teaching you fluid mechanics, each chapter one by one. Okay, I think I will be taking 5 to 6 classes where I will be discussing each chapters, some few important chapters. Okay, so those classes I will take from 31st of December. So from 31st till I think up to 4th of January I will be taking 5 to 6 classes on fluid mechanics. Okay. Come on everyone, tell me the answer quickly. Yes. So the discharge is given in this question. The discharge is equal to 300 liter per second. That will be equal to 0.3 meter cube per second. So discharge is equal to area into velocity, average velocity. So average velocity you can get from here, that is equal to discharge per unit area. So you'll be getting the average velocity. Area is also given here, my dear. The diameter is given 30 centimeter. So you can simply find the area, which is equal to pi by 4 into 0.3 square Just put the value, will be getting the average velocity. Average velocity will be getting as 0.424 meter per second. Now you know that shear velocity is equal to average velocity into root of f by 8. I have just told you formula for the shear velocity. So you can simply say that average velocity is equal to shear velocity is equal to average velocity in terms of that. Uh, Average velocity is equal to 4.24 root of f, that is 0.0097 divided by 8. So you will get the value of shear velocity from here. The shear velocity will be equal to 0.147 meter per second. Clear? So you have got the value of shear velocity. My dear Appan Raj, whatever I am teaching you, it is as per the syllabus, and I am teaching you what is important. Whatever query you have regarding the shear stress variation, I have just told you how the shear stress varies. In the turbulent flow, the variation of the shear stress is very, they are not going to ask this shear stress formula, okay, in the exam, how the shear stress vary in the turbulent flow, because the variation of the shear stress is very, random, or we can say it is, we can say there are different hypotheses given for the variation of the shear stress. Shear stress can be written in terms of, by Bosonic hypothesis, the shear stress relation is different. By the hypothesis of parental, it is different. So every person has given different types of hypothesis for shear stress. If you are having some questions regarding that, you can cover that question in the individual lecture of this turbulent flow in the pipe or plate. Right now, I am also telling you that same thing upon Raj, my dear, because there is the relation of the turbulent shear stress. It is totally different. Okay. Even we don't study that. If you study that thing, the relation of the shear stress, I will tell you, don't worry, just wait for one few seconds. Okay, let us solve few questions first. The maximum velocity minus the average velocity divided by the shear velocity. This is one relation, very important relation. It is equal to 3.75. This is also one important relation. Okay, this relation is also very important. So you have to find the maximum velocity, you know the average velocity, and shear velocity. You can simply say that maximum velocity minus the average velocity is given in this question, that is 4.24, divided by shear velocity is 0.147, is equal to 3.75. So from here you can get the value of maximum velocity. This is an important relation. It will be 4.795. Maximum velocity will be equal to 4.795 meter per second, approximately 4.8. Next question is the velocity in a 60 centimeter pipe carrying oil are 4.5 meter per second at 4.2. Yes, quickly answer the question, everyone. Yes, everyone, quickly answer the question for this. Yes, come on everyone, tell me the answer for this question. Yes, 4.798 has been given by Shivani. Yeah, for that question it is 4.798. For this question, what is the answer? Yes, the maximum velocity is given in the question. If the velocity in a 60 centimeter pipe carrying oil are 4.5 meter per second, 4.2. So central line velocity is also called maximum velocity. Central line means maximum velocity, that is equal to The maximum velocity is equal to center line velocity, which is 4.5 meter per second, and radial velocity, that is velocity at distance of local velocity at r is equal to 10 centimeter, is 4.2 meter per second. You have to find the discharge. How can you find the discharge in this question? Yes, come on, tell me. Yes, very good. The last question, the answer is correct. You have to use this relation. We'll be using this relation u minus u maximum divided by shear velocity is equal to 5.75 log base 10 of y by r. So this relation will be using for solving this question, y by r, this relation. So if you use this relation, the local velocity is given, maximum velocity is given, shear velocity you can find by using this relation. Come on, tell me the answer for this question quickly. So y is equal to pipe radius, y is equal to 0.2. In this question it is given pipe. What is the value of y? So we are having a 60 centimeter pipe. 60 centimeter is the pipe. So radius of the pipe will be equal to what? Radius will be equal to 30 centimeter. And the distance from 10 centimeter from the axis. 10 centimeter from the axis at a local radius of 10 centimeter, the velocity is equal to 4.2. Let us say the y. What is the value of y? The y will be equal to r minus r. So y will be equal to r minus r will be equal to 30 minus 10 will be equal to 20 centimeter. So this will be equal to 4.2 minus 4.5 divided by shear velocity is equal to 5.75 log base 10 of y is equal to 20, that is 0.2 divided by r is equal to 0.3. So just solve this, you will be getting the value of shear velocity. What is the value of shear velocity you will be getting? Yes, shear velocity will be 0.2693. 0.2693 will be the value of shear velocity. Then you will be using this relation. I have told you in the last question that maximum velocity minus average velocity, divided by shear velocity is equal to 3.75. So from here you will be getting the average velocity, because maximum is known to you, shear you have got from here. You can use this relation to find the average velocity. ठीक है, तो average velocity कितनी आ जाएगी आपकी? You will be getting average velocity as 3.389 meter per second. Because you have found the average velocity, you can find the discharge is equal to area into average velocity. That will be pi by 4 into 0.6 square into 3.389. So you will be getting the discharge very easily from here. That will be 0.958 meter cube per second. Y distance क्या है? Y is the distance from the pipe wall. So because the local radius was r and this was equal to 30, so distance from the pipe wall will be equal to what? Distance from the pipe wall will be equal to r minus r. Okay. Next is the concept of the boundary layer. Let us quickly cover the bound, because we have got very limited time today, and if we are not able to cover the hydraulic turbines, then don't worry. I'm very much sure that we are going to cover the dimensional analysis. Complete fluid mechanics will be completed. If hydraulic machinery is not completed anyhow, then in the qualified series I will cover the hydraulic machinery. Okay, because our time is limited today. Okay. Now what is boundary layer? Whenever a fluid start to flow over a plate, over a flat plate, suddenly you will notice that the fluid particles which are near to the boundary, near to the plate, they will be having the velocity of the plate, that is no slip condition will be applied. Okay. So the fluid particles which will be near to the plate, they will start to cling over the plate. Okay. But as the fluid start to proceed above the plate, you will find that there suddenly the velocity gradient will appear. What will happen? Some velocity gradient will start to develop. Okay, so this velocity gradient will appear up to a point which is called as boundary layer thickness. At this point, the velocity will become equal to 0.99 times of free stream velocity. If you join these points of 0.99 times of free stream velocity, you will be getting a layer, and that layer is called as boundary layer. Okay, so whenever a flow takes place over a surface, you will be finding this type of boundary, growth of a boundary over the surface, that is called as boundary layer. Okay, clear everyone? Now initially you will be getting a laminar boundary layer, then it will be transition, and then it will be turbulent boundary layer. So for a flat plate, it will be laminar when Reynolds number is less than equal to 5 × 10⁵. It will be turbulent when Reynolds number is greater than 10⁷, and if it is between both, it is called transition. Also, we in the laminar layer will be having a laminar sublayer. I have already told you what is the laminar sublayer. In the turbulent region also, we have a little bit layer of very close to the plate will be having a thickness of laminar sublayer because of viscous nature of the flow. Because of the viscous nature of the flow near to the plate in the turbulent region also will be having a very small thickness, that is called thickness of the laminar sublayer. I have told you the formula of the thickness of the laminar sublayer in the turbulent flow. Okay. So my dear students, so near to the boundary, just above the boundary in the vertical direction, this boundary layer thickness will grow. This is the lambda. Lambda is the thickness of the boundary layer. So as you move away from the plate, you will be seeing that the thickness of the boundary layer is directly proportional to the square root of the distance from the plate. This is for the laminar flow. For laminar flow, the boundary layer thickness is directly proportional to root of the distance from the leading edge. And for turbulent flow, it is directly proportional to x power 4/5. This is the relation of the turbulent boundary layer thickness. So turbulent boundary layer thickness is directly proportional to turbulent flow thickness. Turbulent boundary layer thickness is directly proportional to delta x power 4/5, where x is the distance from the leading edge. And the laminar boundary layer thickness, in the laminar region, the laminar boundary layer thickness is equal to delta is directly proportional to root of x. Okay, clear everyone? This is a very important relation I have to tell you now. I have to tell you some important relation. In the boundary conditions, the stresses which are not present in the free stream. See, it is very important concept. See, near the wall, the shear stress will be equal to, at the wall, at the plate, the wall shear stress will be equal to mu times of du/dy at y is equal to 0. So these shear stress will be present only in the region of velocity gradient. Where velocity gradient will be there, only there will shear stress will be there. But in the just when the flow will reach at this point, when u will be equal to 0.99 times of free stream velocity, at this condition the velocity gradient will become 0. So when velocity gradient will become 0, the shear stress will also become 0. So the shear stress will only be there in this region. And the wall shear stress is equal to mu times of du/dy at y is equal to 0. At this condition, the wall shear stress will be there. Okay. So there are some boundary conditions that you have to remember in the for solving the problems of the boundary layer. You have to remember this boundary condition at y is equal to 0, u is equal to 0. This is called no slip condition. This is also called no slip condition. At y is equal to delta, that is when y becomes delta. In that condition, u will become u infinity or 0.99 times of u infinity or free stream velocity. U infinity is called free stream velocity. At y is equal to delta, at this particular condition, the velocity gradient becomes 0, and so the shear stress becomes 0. At x is equal to 0, that is at the start of the plate, when the flow is about to start, delta will be 0. Okay, but these are the major boundary conditions you have to remember. These three are the three boundary conditions you have to remember. Okay, Shivani, I have told you about the stresses. These are the stresses that will be present, wall shear stress. Okay, boundary layer thickness is defined as the thickness, it is a vertical distance from the boundary in which the velocity gradient exists, or it is also defined as the vertical distance from the boundary up to the point where velocity becomes 99% of the free stream velocity. That is called boundary layer thickness. At y is equal to delta, u will become 0.99 times of free stream velocity. Now there are three types of thickness in the boundary layer thickness. Why we are using these three types of thickness? The reason is very simple, because boundary layer growth is a phenomenon that we don't want. No fluid wants the flow to be having a boundary layer, but ideally if the flow will be taking place over a plate, then this is how the velocity profile will be. This is the ideal fluid. So ideal fluid will not be having any type of velocity gradients. But when a real fluid will be flowing over a plate, what will happen? It will be having these type of velocity gradient, and because of that there will be a boundary layer growth. Okay, so because of this velocity gradient, there will be some loss in mass flow rate. There will be some loss in momentum, and there will be some loss in kinetic energy. So these losses will take place because of the boundary layer. For a real fluid, this will be the flow. This is how the flow will take place over a plate. But for an ideal fluid, there will be no velocity gradients. So in the ideal fluid, there will be no boundary layer. So the flow, the complete fluid profiles will be there. Fluid profile will be there. So there will be no loss of the mass flow rate. There will be no loss of the momentum. There will be no loss in the kinetic energy. So this concept will not be used. But in order to compensate for these losses in the real fluid, in the ideal fluid, we will be using these three types of thickness. Displacement thickness is to compensate loss in mass flow rate. To compensate for loss in mass flow rate, we will be using the displacement thickness. It is equal to 0 to delta of 1 minus u by u infinity of dy. U by u infinity, it is the velocity profile. It is also called the velocity profile. Okay, so this velocity profile will be given in the question. You can use this relation to find the value of the displacement thickness. Momentum thickness is defined as momentum thickness is equal to the vertical distance by which the solid boundary must be shifted in case of ideal fluid to compensate for the loss of momentum due to boundary layer. So this is the formula for momentum thickness, and the energy thickness is given by this formula. These are the formula for energy thickness, momentum thickness, and all distribution thickness. Clear, everyone? One more important thing is that displacement thickness will be more than the energy thickness, and energy thickness will be more than the momentum thickness. So least will be the momentum thickness, maximum will be the displacement thickness, then energy thickness. Okay, this is how the thickness will vary. Okay, now next term is called shape factor. It is also called ratio of displacement thickness divided by momentum thickness is called shape factor. Flow over flat plate will be using von Karman equation. It is equal to wall shear stress divided by rho v infinity square is equal to d theta by dx. Theta is the momentum thickness, rho is the density, v infinity is the free stream velocity, tau naught is the wall shear stress. This is called as von Karman momentum integral equation. Then we are having using the concept of drag. This is also very important. The drag force is equal to half of CD rho a v infinity square, and the wall shear stress is equal to local drag coefficient divided by half rho v infinity square. These are the two formula which are important. Okay, so local and average skin friction coefficient, CDX is called local skin friction coefficient. This is called local wall shear stress. This is important formulas. Okay. Last concept is boundary layer separation. Boundary layer separation basically takes place because of the positive pressure gradient. So because of the positive pressure gradient, you must have noticed that why the shape of the every automobile is designed in a very special way. Why? Like you can see Hyundai car or Honda car, so you can see the BMW, Mercedes, they have different shapes. They have different streamline shape. Or also if you see the aeroplane, it is also streamlined different types of shape. Why they are giving a different type of shapes? The main reason is to suppress the boundary layer separation. So boundary layer separation is basically a phenomena in which the flow will separate from the boundary over which the flow is taking place. What is the condition of boundary layer separation? So initially, when the flow takes place over a surface, there will be positive velocity gradient. du by dy will be positive and pressure gradient will be negative. This is the condition for attached flow. Okay, so flow will remain attached over the surface. So there also comes a point which is called separation point. Separation point is that point. Separation point is that point when du by dy becomes 0 or pressure gradient becomes 0. That is called separation point. And the last point is called when the flow will become separate or when backflow take place. Backflow कब हो सकता है? Backflow takes place when suddenly the pressure in the moving direction, the pressure will increase. So the flow which was taking place in this direction, suddenly the flow will reverse. This will happen due to positive pressure gradient. When pressure gradient becomes positive and velocity gradient becomes negative, this is a condition of separation. This is a condition of separated flow. Okay. So always remember that the flow will separate when the positive gradients will take place, positive pressure gradients will take place. How can we control the boundary layer separation? You can control the boundary layer separation by accelerating the flow in the boundary layer, by suction of the slow moving fluid in the boundary layer, streamlining the body. That is why the car bodies are streamlined, keeping the divergence angle to minimum. This is why in the Venturi meter the divergence angle was kept less than 7 degree in Venturi meter to suppress the boundary layer separation. Okay. When pressure gradient is positive, yes, exactly. Rotating the boundary in the boundary layer region or supplying additional energy from blower. So these are the methods for suppressing the boundary layer. Now let us solve few questions. Quickly solve the question because we have to cover the dimensional analysis also. That is the last topic, and hydraulic turbines, I don't think we will be able to cover the hydraulic turbines. So, but it is very sure that your mechanics subject will be completed. Machinery will not be completed, but don't worry, machinery I will complete in the qualifier series. In the qualifier series, I will take classes of hydraulic turbines. In that, I will complete the revision of complete hydraulic machinery. Okay. So if you think that machinery is not getting completed, don't worry. I think around 2nd of January or 3rd of January, I will take the class of hydraulic turbines at 11 p.m. in the qualified series. There I will complete the topic of hydraulic turbines. Okay. So boundary layer thickness at the trailing edge of the flat plate is 15 cm wide and 45 cm long, placed or longitudinally in a stream of oil of radial density 0.2500. Okay. You have to find the boundary layer thickness simply. Yes, come on everyone, quickly tell me the boundary layer thickness. One more important thing, why I have missed this thing, delta is equal to 5 into x by root of Reynolds number for laminar flow. For laminar flow, this is how the boundary layer thickness varies. So boundary layer thickness is directly proportional to root of x from here. And for turbulent flow, the boundary layer thickness is equal to, for turbulent flow, the boundary layer thickness is equal to 0.79 into x or Reynolds number over 1 by 5. Also, boundary layer thickness is directly proportional to x power 4 by 5 for turbulent flow. Okay, clear? So for turbulent flow it is this, and the shear stress is directly proportional to 1 by root of x. This is how the shear stress vary with the distance from the leading edge. So tell me the answer for this question quickly. Come on everyone. So this equation is also called as Blasius equation. From Blasius equation you can find this. Blasius equation you can directly find the value of the thickness of the boundary layer for laminar flow. Okay. This is how you can find the thickness of the boundary layer for turbulent flow by Blasius equation. Yeah, you can also write it as 4.95 x by root of Reynolds number. It is not going to change it. It is approximately equal to 5x. Okay. Yes, come on, tell me everyone, how can you solve this question? You have to find the Reynolds number first. It is equal to u into L by nu. It is equal to u is the velocity which is given 6, free stream velocity into L is given as 45 centimeter, that is 0.45, divided by nu is equal to the kinematic viscosity. So they have given the value of relative density is equal to this. Kinematic viscosity is 0.9 stoke, that is 0.9 into 10 power minus 4. So you can simply find the value of Reynolds number. You can get this value as 3 into 10 power 4. This will be the Reynolds number. Because Reynolds number is less than equal to 5 10 power 5, it is a laminar flow. And because it is a laminar flow, you can simply use that relation delta is equal to 5 into x by root of Reynolds number. Okay, so 5 into x. What is the value of x here? X is given as 4.5, 45 centimeter. Or this is equal to 5 into 0.45 divided by root of 3 into 10 power 4. We will simply get the answer. You will be getting the answer as 1.3 meter. Sorry, 1.3 centimeter you will be getting. Okay, clear everyone? Next question, air having kinematic viscosity of 15 10 power minus 6 with a free stream velocity of 10 meter per second flows over a smooth dimensional flat plate. If the critical Reynolds number is 5 into 10 power 5, what is the maximum? Critical Reynolds number क्या होता है? Critical Reynolds number for a flat plate is equal to that Reynolds number after which the flow will change from laminar to turbulent. So it is equal to 5 into 10 power 5 for a flat plate. This is the critical Reynolds number. Okay. So you have to tell the maximum distance up to which the laminar boundary layer will exist. Come on, tell me. It's a very simple question. Reynolds number is given. It is equal to V infinity into x by mu. The kinetic viscosity is given. Length of the plate is also given or not. So you have to find this. You have to find maximum distance up to which this will exist. So x you have to find this question. It is a very simple question. Come on, tell me. Come on, tell me everyone. Gaurav has given 75 B. Good. The answer will be 75 centimeter B. So this will be equal to 5 into 10 power 5 is equal to 10 into x divided by 15 into 10 power minus 6. So x will be equal to 75 centimeter. Good, very good. Gaurav, good. Next question, a rectangular plate, flat plate 0.5 into 1.2 meter is to be set at right angle to the flow of water in a river. If the design velocity of the flow is 2.5 meter per second, then the force in kilonewton required to hold the plate at the rest is. This is the drag coefficient. Drag coefficient is equal to 1.2 and density is equal to 1000. Come on, tell me the answer for this question. Simply you have to find the drag force. Drag force, I told you the formula, it is equal to half of CD into rho A U infinity squared. This is the formula for drag force. Everything is given, the velocity is given. Area you can find by using this, multiplying these two things, you will be getting the area. And CD is also given. Everything is given, just put the value, you will be getting the value of drag force. Tell me the answer, everyone. Yes, what will be the value of drag force? Quickly tell me. Gaurav Vajpayee has got B as the answer. Yes, hurry up. Hurry up, we have to cover one more chapter of fluid mechanics, the last chapter of fluid mechanics, that is dimensional analysis. At least we should revise the entire fluid mechanics, not hydraulic turbines, because turbo machinery is a part of fluid mechanics. So I wanted to revise turbo machinery also, but because we don't have much time, so today the timing is limited. Because I have some important work to do also. Yes, come on everyone. The drag force will be equal to what? Half of CD. CD is 1.2 into 1000 into 0.5 into 1.2 into 2.5 square. The answer will be 2.25 kilonewton. Are you getting option B? Yes. Abhay Kumar, Shiva Tribe, Shivani, Gaurav, very good. Next question, a flat plate is kept in an infinite fluid medium. So we have to definitely match the column 1 and column 2. Quickly answer the question. Come on. You have to do match the following in this question. Hurry up. We are having a rectangular plate and we are having a flat plate. In the column 1 you can see that for laminar boundary layer on the plate, pick the correct option between 1 and 2. The boundary layer thickness increases in the flow direction or decreases in the flow direction or remains unchanged. Shear stress, pressure gradient along the plate. Hi, Gaming with Atri, very good evening. Welcome to the session. Those who have recently joined me for the session, please do not forget to like the session also. Please also like the session. Come on everyone, quickly tell me the answer for this question. Boundary layer thickness in the laminar flow, it is directly proportional to root x. So it will increase, if x will increase, it will increase. Shear stress in the laminar, it is inversely proportional to root x. So shear stress will decrease if x will increase. Okay. So this boundary layer thickness will be 2, this will be 1. So for P it will be 2, for Q it will be 1 and this will be 3. So this will be 2, 1, 3. The right answer is option D for this question. Okay, the right answer will be option D. It is not C. Boundary layer thickness will increase in the flow direction in the laminar flow. The shear stress will decrease in the flow direction. Yes, for P it is 2. But for Q it is not 2, it is actually 1. Shear stress will decrease in the flow direction, boundary layer will increase in the flow direction, and the pressure gradient will be constant. Next question, flow separation occurs when? Flow separation occurs when dV by dy is less than 0, pressure gradient is less than 0, velocity gradient is positive or pressure gradient is positive. What is the answer? When can we say the flow separation will occur? Come on, quickly tell me the answer. We have to revise the dimensional analysis also. Hurry up. The flow separation will occur when velocity gradient will be negative or positive or pressure gradient is negative or positive. When can we say the flow separation will occur? Flow separation occurs, or flow will get separated actually they have to write the question in this way. The flow separation occurs when flow separation कब हो जाता है? When velocity gradients are negative and pressure gradients are positive. Okay, so the answer will be option A and D. Very good, Gaurav, Abhay Kumar, Deepak Kumar, very good. Now the last topic of revision is dimensionless analysis. See, dimensionless analysis is basically a method of dimension. It is used for conducting research work, for conducting model tests. Basically in that we will be dealing with different types of dimension. The mainly 3 major dimensions are length L, mass M and T. We can say these are the 3 fundamental dimension M, L, T. M is for mass, L is for length and T is for time. Now from this fundamental dimension we can derive some secondary dimension which are for velocity it is Lt minus 1, for density is ml minus 3, for acceleration it is Lt minus 2. These are called secondary dimension. For example, area dimension is L square, volume is L cube, velocity is Lt minus 1, angular velocity is T minus 1, acceleration is Lt minus 2, angular acceleration is T minus 2, discharge is L cube T minus 1, acceleration due to gravity is Lt minus 2, force is Mlt minus 2, weight is Mlt minus 2, dynamic viscosity is Ml minus 1, T minus 1. Velocity gradient is not 0, Shivani, velocity gradient is negative. When pressure gradient becomes positive, velocity gradient becomes negative. Okay, that is the condition of flow separated. Okay, kinematic viscosity dimension is L square T minus 1, pressure is Ml minus 1, T minus 2, surface tension is Mlt minus 2, so work energy is Ml2 T minus 2 and power is Ml2 T minus 2. So these are the dimensions. You will get the table for different dimensions. So for dimensional analysis there are 2 methods. One is called Rayleigh method, one is called Buckingham pi theorem. Rayleigh method is a method which is used for dimensioning. For example, if you have to find the relation T is equal to 2 pi under root L by G. So this type of relation basically you can write by using the Rayleigh method, because we are using 3 relation T, L and G. 3 variables are there. So when we'll be having 3 or 4 variables, we'll be using Rayleigh method to find the relation between different types of variables. So Rayleigh method is a method which is used for finding the relation between different variables to write these types of correlations like time period of oscillation and different other types of relation. Rayleigh method is a method, but it is used only up to 3 or 4 variables. Next method is Buckingham Pi theorem. This method is used for n number of variables. So for n number of variables, we'll be using the Buckingham Pi theorem. Okay. Let us say there is a equation in which we have n variables are there. N means it can be 7, it can be 6, anything. And m is equal to 3. M is the fundamental dimension. So according to Buckingham Pi theorem, how many times of dimensionless group can be formed? We can form n minus m is equal to pi terms. Pi dimensionless terms can be formed, and by using these pi terms we can find the relation. Like this relation, we can find the relation here also, but Buckingham Pi theorem is used for more than 4 variables. If we have to find the relation for more than 4 variables, we'll be using Buckingham Pi theorem. Now, in dimensionless analysis, we have different types of forces we study. Inertia force, it is also called pseudo force. You have studied in the engineering mechanics. It is just opposite to the, it is equal to mass into acceleration, and it is just opposite to the force. Like let us say we have applied a force on an object. So object will be moving in this direction. So opposite to this force will be having an inertia force which will try to oppose this motion. That is called force of inertia. It is best explained in the D'Alembert principle you have studied in the engineering mechanics. So inertia force is equal to rho L V square. Rho L square V square. This is inertia force. Let me write it again. It is equal to rho L square V square. Next is the surface tension force. Surface tension force is equal to, because surface tension is equal to force per unit length, so surface tension force is equal to product of surface tension length. Next we study gravity force. It is equal to mass into gravity. It is equal to rho L cube into G. So gravity force is equal to rho into L cube into G. This is gravity force. Next we study the pressure force, because pressure is equal to force per unit area. So pressure force is equal to pressure into area. So pressure force will be equal to pressure into area. Area dimensions क्या होते हैं? L square. This will be the pressure force. Viscous force will be writing as mu into LV. Viscous force will be equal to mu into V into L. Elastic force is equal to product of elastic stress into area. Elastic stress in area. So it is equal to K into L square, where K is the bulk modulus of elasticity. So product of bulk modulus of elasticity and area is called as elastic force. So by combining these different types of forces, we get different types of dimensionless numbers. Reynolds number is the ratio of inertia force to viscous force. This Reynolds number is used for the application of pipe flow and fully submerged flow. Reynolds number is equal to rho VL by mu, or it is equal to VL by mu. You know about the Reynolds number, right? Froude number. Froude number is used in the application of spillway, notches, wear. These are the application of the Froude number. Okay, hi Krishna Yadav, good evening, welcome to the session. So Froude number is equal to V by root LG. This is how we write the Froude number. Okay, where L is the length, G is the acceleration due to gravity, V is the velocity. Euler number is used for the study of cavitation phenomena. Euler number is equal to ratio of inertia force by pressure force. Inertia by pressure, and that to root of that. Froude number is equal to ratio of inertia by gravity force. Okay, so Euler number is equal to V by under root P by rho. Then we are using Weber number. Weber number is equal to root of inertia force by surface tension force. Inertia by surface tension. Square root of inertia by surface tension force is called as Weber number. And Mach number is equal to ratio of inertia force by root of inertia force by elastic force. Inertia force by elastic force. मेरा नाम क्या है? Hi Ajay Chauhan, I am Vikas Sir. Welcome to the session. Okay, so Mach number is equal to V by C, where V is the velocity of the fluid, C is the speed of sound. This Mach number is very important. See, speed of sound is equal to under root of K by rho. This is the speed of sound is equal to root of K by rho. Okay, so these are the different types of number, dimensionless number. But what is important for you in dimensional analysis is model laws. Different types of models law we use. Two model laws are very important: Reynolds model law and Froude model law. Reynolds model law is used in the application of pipe flow and the resistance experienced by submarine, airplane, fully immersed body. In this application, we use the Reynolds model law. So in the Reynolds model law, we will be simply using this. Reynolds number of model will be equal to Reynolds number of prototype. We'll be simply using this in Reynolds model law. Okay. Hi Ramesh, welcome to the session, my dear. Good evening, Krishna Yadav. Good evening. So Reynolds model law, why we use this model law? Basically, model law are basically used for conducting some test on the models. Suppose that you must have in your BTech, you must have worked on some project, final year projects. Now these projects are simply the replica of the, they are not actual working thing, right? They are not, suppose if you are making the model of a aeroplane, so it is just a model, it is not the actual aeroplane, right? If you are making the model of a turbine, it is just a turbine, it is not the actual turbine, right? If you are making the model of a windmill, it is just a model, it is not the actual one. So actual one is called prototype. Actual product is called as prototype. And the replica of this, replica of prototype, replica matlab iska copy. Replica of prototype is model. Okay, so we have to find the relation between model and prototype. So good evening everyone, those who have just joined me in the session, and those who have joined me, Kabir Beg, hi, good evening, Krishna Yadav, Ramesh, Ajay Chauhan, please do not forget to like the session also. So suppose we have to find the relation between model and prototype, and that too for the flow in the pipe and flow in the submarine, aeroplane, fully immersed bodies. In those applications, we can simply say that Reynolds number, which is rho VL by mu of model, will be equal to rho VL by mu of prototype. What is the advantage of finding this relation? The simple advantage is that we can find the value of the velocity, length, and other things for the model, and by finding that these results on the model are correct and we are getting some correct result, so based on that we can basically replicate that over the prototype, right? Suppose we have got good result on model, so we can understand, okay, we just have to do the scaling of that model, and by using same principle we can make the actual prototype. Okay, so this is what Reynolds model law is. We have to just equate the Reynolds number of model and prototype, and by equating it, they can give you the value of velocity of the prototype, they can give you the velocity of model, they can give you the length of the model, they can give you the length of the prototype, and they can ask you any of this thing. Okay, maybe they have given you velocity of prototype, they can ask you velocity of model, or they can ask you to find the length of the model of prototype. Okay, so you can use this formula. You can simply use this formula: density of the model into velocity of the model into length of the model divided by mu of the model is equal to density of the prototype into velocity of the prototype into length of the prototype divided by mu of the prototype. This is a simple formula, but this formula is only used in the application of pipe flow and flow through submarines and other application. Okay. Well, Ramesh, today I won't be able to cover the velocity triangle because I have very less time today. So velocity triangle will not be possible to cover today, but I will cover the hydraulic turbines in the qualified series that take place at 11 p.m. in the night. So in that qualified series, I will take the hydraulic machinery. Okay. Next model is Froude model law. Froude model law is basically used for application of free surface when the flow takes place over a flat plate, flow over plate. In application of flow over plate, free surface, spillway, notches, weir, sluice gate, channels, flow through jet. In all these applications, we use the Froude model law. In Froude model law, we just have to equate the Froude number of model and prototype. So here we'll be using Froude number of model will be this. Froude number of prototype will be equal to this. So it is very obvious this will get cancelled out. So we can say that we'll be getting a relation that Vp by Vm. we'll be getting Vp by Vm. This is velocity of the prototype by model is equal to root of Lp by Lm. This root of Lp by Lm, root of Lp by Lm is also called as scale ratio, and it is equal to Lr, length ratio for scale. So what I'm going to tell you here is very important. In your question, they will give you the value of length of model by prototype. In the question, in exam, they will give you length of model by prototype or diameter of the model by prototype in the exam. Okay. So what you have to do, you have to convert that into Lp by Lm. So they will give you like 1 by 20 or 1 by 40. So you have to understand this is the length of model by prototype, not Lp by Lm. Because length of the prototype will always be greater than model. Okay. So always remember that they will give you the scale ratio. Sometimes they give you opposite scale ratio. They will give you Lp by Lm, sorry, Lm by Lp or Dm by Dp in the exam. So you have to convert that into Lp by Lm. To find the velocity ratio is equal to root of length ratio. It is very important. Similarly, so we have got velocity ratio. Velocity is equal to Vp by Vm. So Vp by Vm is equal to root of Lp by Lm. Acceleration का भी same ratio आता है. Acceleration का क्या आता है? Acceleration AP is equal to AM. Acceleration of the model is equal to acceleration of the prototype according to Freud model. Time period of prototype by time period of the model is equal to root of length of the prototype by length of the model. Time period का ये relation होता है. Discharge का क्या relation होता है? Discharge of the prototype by discharge of the model is equal to Lp by Lm of 2.5. If dm by dp is given, you have to convert it into dp by dm. Okay. See, whether you write ln by lp or dm by dp, it is same thing. Okay. Anything is given, you have to take it as, okay. This is the scale ratio for length, or you can say scale ratio for any length quantity, which is geometric quantity. It can be length, it can be diameter, it can be height, anything will be there. Okay. Similarly, force of the prototype by force of the model is equal to Lp by Lm Q, and the power of the prototype in power in the model will be equal to Lp by Lm 3.5. So these are some important relations you have to remember, my dear students, for solving the problems. Now let us solve few problems and let us end the session, because I cannot extend the session much. I cannot cover the hydraulic turbines because there is a limitation of timing. I am taking a lot of extended session, which is definitely not allowed. I cannot take much bigger sessions. Okay, already I am taking bigger sessions now, and very lengthy sessions. Okay, it is not allowed. So, but fluid mechanics is completed with complete numericals. It is completed. I have taken question from each chapters. Each chapter's question have been taken in this revision session. Only hydraulic machinery is not completed, but I promise you I will complete the hydraulic machinery in the qualifier series. A ship model of 1 by 40. What is the meaning of this? That is Lp by Lm is not given. Lm by Lp is equal to 1 by 40 given. So Lp by Lm will be equal to what? 40. Is towed through sea water at a speed of 2 meters per second. So speed of the model is equal to velocity of the model is 2 meters per second. A force of 2.5 Newton is required to tow the model. Force of the model is equal to 2.5 Newton. The propulsive force on the ship in kilonewton in the prototype is subjected to wave resistance only. You have to find the force in the prototype in kilonewton. So come on everyone, quickly tell me the answer for this question. So I have just told you that the force of the prototype by force of model is equal to length of the prototype by length of the model Q. You know this relation? This is given 40, so this is 40Q is equal to Fp by M. This. So force in the prototype will be equal to 2.5 into 40Q. So we'll be getting this answer as uh, 160 kilonewton. So you'll be getting the answer in Newton. You have to divide by 1000 to get into kilonewton. Okay, clear everyone? So you'll be getting 160 kilonewton. Next question. In a model built on Freud law of a similarity of phenomena lasts for 20 minutes. So in a model, the phenomena is taking how much time? Time in the model is 20 minutes. If the model scale is 1 by 25, that is length of the model by prototype is equal to 1 by 25. So LP by LM will be equal to what? 25. You have to find the duration of the phenomena in the prototype. Yes. Come on, tell me the answer for this question quickly. I have told you that time in the prototype by time in the model is equal to root of LP by LM. Okay. So my dear students, this is given. It is very simple. It is root of 25, that is 5. So TP will be equal to TM into 5. That is 20 into 5. It is 100 minutes. Very simple question. Very simple question. The answer will be option B. Have you got the answer, everyone? Tell me quickly. Be quick. Have you got the answer? Everyone. Yes, everyone has got the answer. Good, good, good. Next question. 500 kilowatt power generated by a large hydraulic turbines at 1000 rpm under a head of 40 meter. A 1:5 scale model, that is LP by LM, will be equal to what? 5. Turbines operate under a head of 10 meter. Power generated by the model is. The power of the prototype by power of the model is equal to what? LP by LM power 3.5. Very simple. You just have to use this relation. If you know the relation, the question will become very simple for you. Okay. You have to find the power of the model. Power of the prototype is 500 kilowatt. Divided by power of the model is equal to 5 power 3.5. So power of the model will be equal to 500 divided by 5 power 3.5. So tell me the answer quickly, everyone. Come on, be quick. Be quick, my dear students. 5 power 3.5 क्या होगा? What will be the value of 5 power 3.5? Okay, they have given the head also here in this question. Okay, little bit. This question is little bit different. Are you getting the answer? What is 5 power 3.5? 5 power 3.5. Tell me. They have given the speed also in this question 1000. The head is given. Then okay, these are relation are different. Okay, this question have to be solved. 5 power 3.5 कितना होगा? जल्दी से बताइए. What is the value you are getting? It's B. Actually, this question can be solved by two relations. Okay. So basically, if you solve it, how much answer you'll be getting? You'll be getting approximately 2 kilowatt, right? But you can use this method. You can use another method here, and that method is because whenever a turbine is given here, so you'll be using a different relation here in this case. So what is the relation you'll be using here? It is very simple. 1 point root of head of the model divided by D into N. Okay, this is the relation you'll be using here. I think the answer will be approximately, you can use approximately, it will be See, this method can be solved by this method also. Okay, both the methods can be used. Head of the prototype divided by dp into np. So you can simply find the value of the speed in the model. Speed in the model will be equal to root of hm by head of the model by prototype into dp by dm into np. If you solve it, you will be getting the value of nm. Speed of the model will be equal to what? Speed of the model will be equal to 2500 rpm. Now we can use one lone relation, that is p by d5 n cube. This is also relation C. By using these relation, you can also solve the question that power of the prototype divided by diameter. This is P m m m. By using these relation also, you can find the power of the model will be equal to power of the prototype into dm by dp 5 into nm by np cube. You can use this relation also to find the power. You will get getting 2.5 kilowatt. So okay. So by here you will be getting 2.5 kilowatt by using this relation. By using this relation you will be getting 2.5 kilowatt because this type of question is important. Okay. If you will be using model prototype relation that I have taught here by fraud model law, you will be getting the answer as approximately you will be getting 1.78 kilowatt or approximately 2. Okay, but here is nothing they have mentioned that it is a fraud model. They have not mentioned it is a fraud model law. Because fraud model law is not mentioned here, so you cannot directly use this formula. In that condition, you have to use this approach. Firstly, you have to find nm, speed of the model, then you have to find this. So the answer will be option A in this question. Clear? Next question, which is the second last question. Hurry up. A 1:5 model of a parachute needs to be studied in a wind tunnel. The actual parachute carries 80 kg load and lands at a speed of 18 km per hour. The drag force experienced by the parachute under, what is the diameter? See, it is not a diameter. It is, see, you can call it as dp by dm. It is up to you. You can call dp by dm or you can call lp by lm. Okay? Yeah, it is same. You can call it as lp by lm or dp by dm. Both are same. Now, this question, a 1:5 model of a parachute in a wind tunnel. See, wind tunnel comes under fully immersed body. It is application of fully immersed condition. And in fully immersed condition, you cannot directly apply the condition of, you have to use Reynolds model law. You have to use Reynolds model law. And in Reynolds model law, you cannot apply the drag force relation. You cannot apply the force relation directly. So here you have to use the formula of drag force. It is equal to half of CD into rho into A into V square. Okay. So drag force will be equal to, this is a constant. It is a constant. It will be equal to L square into V square. So drag force in the prototype will be equal to this. And drag force in the model will be equal to this. Okay. So in this question, they have given that a 1:5 model scale, that is the length of the prototype by length of the model is equal to 5. So simply you can say that So in this question, you can simply say that the drag force of the model, if you equate this, the drag force, you have to find the value of the drag force experienced by the parachute. Okay. So model of a parachute is tested in a wind tunnel. Actual parachute contains a speed of this. The speed of the actual parachute is given. Yes, tell me everyone, how to solve this question. So drag force of the model divided by drag force of the prototype will be equal to Lm square by Lp square into Vm square by Vp square. Okay. So in this question they have given the velocity here also. Because it is a Reynolds model law, in the Reynolds model law we can use rho Vl by mu is equal to rho Vl by mu. This will get cancelled out because we'll be using this simply that Vm by Vp will be equal to Lp by Lm. Okay, so we can simply say that the velocity of the model is given in this question. Velocity of the model is will be equal to Lp by Lm is equal to 5 into 18. That will be equal to 5 into 18, which will be 90 kilometer per hour. But in meter per second, it will be equal to 90 into 5 by 18. That will be 25 meter per second. So velocity of the model will be equal to 25 meter per second from here. So we have got the velocity of the model by Reynolds model law. We can put this relation here. So we can simply say that drag force of the model divided by drag force in the prototype is equal to drag force in the model is equal to given or not? That is equal to Vp. Lm by Lp is equal to 1 by 5 square into Vm, that is 25 square, divided by Vp. What is dp? It is equal to 5 square. Yes, sir, just solve this question. We'll be getting drag force by model by prototype, which will be equal to 1. This relation will be getting as 1. Okay. Clear everyone? 1 by 5 square. Okay, clear everyone? This will be, you can simply say 25 by 5 whole square. So it will be equal to 1 by 25 into 25. This will be equal to 1. So drag force of the model will be equal to drag force in the prototype. Okay. So this is the result you will be getting here. That is, what is the drag force in the model? It is same as the drag force in the prototype. So what is the drag force in the model? Is it given in the question? It is 80 kg. 80 kg is a drag force. So it is the actual weight. It is a drag force. Now it is a weight. It is 80. Or we can say if g is equal to 10. So that is 80. In the prototype, it is equal to 80 into 10. That is 800. 800 Newton is in the prototype. So in the model, it will be equal to how much? 800 Newton. Are you getting this thing or not? So in the we have to apply the Reynolds model law in this for solving this question. Why we are using the Reynolds model law? Because it is a case of wind tunnel. Wind tunnel comes under the fully immersed body, or a parachute also comes under fully immersed condition. In fully immersed condition, we have to use the Reynolds model law. Okay, so from Reynolds model law, we have found the relation of the velocity of the model, which will be 25 meter per second. Velocity of the prototype was given 18 km per hour, which is velocity of the prototype was equal to 18 into 5 by 18, which is 5 meter per second. That was 5 meter per second. Velocity of the model is 25. Then we can use this relation, drag force of model by prototype. If we solve it, you will be getting this value as 1. How Vikram, what are you asking, my dear? Please ask the question clearly, my dear. How you are asking? Yes, it is a Reynolds model law, भाई. Reynolds model law है density आपकी wind tunnel हो या फिर parachute हो, both are tested in air will be having same density, same viscosity. That will get cancelled out. only relation will be between model and prototype. Beta, that is not that is Vikram, that is fraud model law. Vp by Vm is equal to this. This is the fraud model law. We are discussing about the Reynolds model law. I have applied the Reynolds model law here. Clear or not? We have applied the Reynolds model law here. Let me again write it here. Why we are using Reynolds model? Because parachute and the wind tunnel comes under the fully immersed body. They comes under fully immersed body. So Reynolds model law will be applied here. Reynolds number of model will be Reynolds number of prototype. It is rho VL by mu of model will be equal to rho VL by mu of prototype. Because this hole is tested in wind tunnel and parachute, we'll be using air. So air will be having same property. So this will get cancelled out. So we can simply say that velocity of the model by velocity of the prototype will be equal to length of the prototype by length of the model. Length of the prototype by model is equal to 5. So velocity of the prototype is 5 here. So this velocity of the model will be equal to 5 into 5, that is 25 meter per second. Okay, clear, Vikram? So you will be getting the value of the velocity of the model here. Just put the value in this relation. Velocity of the model is 25. This is this is 5. That will be 25 by 5. That is 5 square. 25 by 25. This will be 1. That is drag force in the model is equal to drag force in the prototype. The actual parachute weight is 80 kg. The weight is not given, mass is given. So weight will be equal to what? 80 into 10, because acceleration due to gravity is 10. This will be 800 Newton. 800 Newton will be there. Okay, my dear. So whatever is the drag force in the prototype, same will be in the model. Okay, last question. Which of the following is correct regarding Euler number? Come on, tell me the answer quickly. Which of the following is correct regarding Euler number? It is significant in the capillary study, significant in the cavitation study, ratio of the inertia force to pressure force, or varies inversely with the square root of pressure force. Tell me. Euler number. Which of the following is correct regarding Euler number? Quickly answer the question. Shivani is saying C for this question. Significant in capillary study, significant in the cavitation study, ratio of inertia force to pressure force, or varies inversely with the square root of the pressure force. Quickly tell me the answer for this question. Vikram is saying C and D. Okay. The answer will be option B and D. Why B and D? Because it is not the ratio of inertia force to pressure force. It is ratio of square root of inertia force by pressure force. See, if you not write it, if you see square root and square, only inertia force by pressure force, it is very different. There is a difference between square root and simply writing inertia force by pressure force. If you simply say it is ratio of inertia force by pressure force, then definitely it is not the Euler number, my dear. It is something else. Okay. So my dear student, with this the topic of fluid mechanics is completed. In 2 classes I have completed the entire fluid mechanics with revision and with 50 plus, around 50 plus question we have discussed in both the classes. Okay. So this is a complete revision with practice in 2 classes. Fluid mechanics is completed. Hydraulic turbines, I thought I will tackle and use, basically I will teach you this, but because we are not having time is already over. So this thing I will teach you, this whole thing I will teach you in the, I have got everything regarding hydraulic machinery also have brought for this session, but because we are not having ample time, because time is over, already 3.5 hours completed. So my dear students, with this fluid mechanics is completed, and hydraulic machinery, don't worry, I will complete hydraulic machinery in qualified series. So hydraulic machinery I will complete in, or hydraulic turbines I will complete in qualified series. So in qualified series, which is starting from 31st, my subject of fluid mechanics will be started 31st December 11 p.m. Okay, 31st December 11 p.m. the qualified series of fluid mechanics is starting. So I will be teaching you. So for all the solutions which were shown regarding, yes Vikram, those were for the fraud law. Okay, those relation I have taught you were only for the fraud law. Okay. So thank you so much, my dear students. Hydraulic turbines topic I will complete in the qualified series will be, which is starting. I will be starting fluid mechanics from 31st. So from 31st till I think next 5 classes I will be taking some topics of fluid mechanics, and in that I will complete hydraulic turbines also. Okay, don't worry. So complete fluid mechanics revision is completed except hydraulic turbines, which I will definitely complete in the qualified series. Okay. You can also join our channel Gradeup. You can join our Telegram channel Gradeup, GATE and ESE /ME preparation. So this is the name of our channel. The link for the Telegram channel. This is the link for the Telegram channel. Okay. So you can join our Telegram channel to get the PDF of this session. Not just PDF of this session, the PDF of the every session that I have taken, thermodynamics, the PDF of the fluid mechanics session that I have taken in the last yesterday, and today's PDF session. So you can take the PDF, you can download the PDF from the Telegram channel. I will upload the PDF. Okay. And also you can follow our Telegram channel to get the video update regarding all the videos. Tomorrow will be the the practice session of thermodynamics, where I will be taking 40 plus important questions of thermodynamics. Okay. So thank you so much. Yeah, definitely. I have, my lecture has extended. I have to complete the lecture at 8 p.m. but it has extended to 30 minutes. So yeah. So now it is extended. So what we can do, but at least your fluid mechanics is completed. Okay, that is a relief that your fluid mechanics is completed. Okay, so that is a relief on me that your revision of entire fluid mechanics is done. Now hydraulic turbines I will take in the qualified series. So thank you so much for joining me for this session. And I can see most of you that 4 dislikes are also there. So guys, if you have not liked the content, then no problem, but please, dislike really hurts me, because no matter whether you, because it is a revision session, I can understand that some of you have not understood some concept, because it is a revision session. I'm in a bit hurry to cover a lot of things, but at least appreciate the hard work that we are putting forward, right? So what is the need of dislike? Dislike means that something you are not liking here in the, as a content. What do you expect to cover in 3.5 hours? I have covered 24 questions, I think, and the revision of all the topics from fluid dynamics to dimensional analysis. What do you expect? So I don't think that I deserve this dislike, guys. So guys, please like the session, share the session to as many friends as possible, and also please subscribe the channel. अगर आपने subscribe नहीं किया है, please subscribe our channel. Thank you so much. I'm going to see you tomorrow for thermodynamics revision, not revision, practice session at 7 p.m. Timing will be 7 p.m. So from tomorrow onwards, I will meet you at 7 p.m. on GATE Gradeup YT channel. Okay, so please note down the timing, 7 p.m. for thermodynamics practice session, where I will be solving 40 plus questions of thermodynamics. Okay, so thank you so much for joining me for today's session. Have a good day and good night. Thank you.